against us. I've been in Boston since 2019, really diving deep on supporting the states up and down the East Coast and now the West Coast understand the requirements for an offshore wind supply chain, and also supporting developers understand where they can invest many of the investment dollars in developing robust and a supply chain that has longevity for the industry. So it's a real honor to present some of the speakers today, and I'm going to ask them to just introduce themselves one by one and give an overview of what they're going to be speaking about today, and then I'll give you a quick overview and set the scene a little bit before they dive into their presentations. So, Ross, do you want to introduce yourself?
Yeah, sure. Hi. Good afternoon, everyone. It's a real pleasure to be here with you all today. Thank you, Jamie. Thank you, National Offshore Wind Research and Development Consortium, for having us. Ross Gould, Vice President for Supply Chain Development and Research with the Business Network for Offshore Wind. I oversee the network's programs related to offshore wind supply chain workforce development, and our policy research work. I am also, and it's my pleasure to be the project lead for the Business Network for our project 30 gigawatt by 2030, a supply chain roadmap, which I'll be getting into more details in a little bit. But for those, I'll leave it at that. I'll introduce the network in a little bit. Thanks.
Hi, my name's Pat Taylor. I'm with Anduril Industries, the Maritime Department. It's good to be back at Northeastern. I'm an alumni, I guess, now, so it's good to be back home. I'll be talking about our fully autonomous, peer-launched AUV, or autonomous underwater vehicle solution that we are funded with the NOWRDC, and we'll dive in when I go through my slide deck. So thanks.
Hey, I'm Atheendra, and I'm a naval architect and hydrodynamic engineer working for MARIN. We are a hydrodynamics and model testing institute based in the Netherlands, and I work out of the Houston office. And we had done a project looking at different feeder concepts that are being considered for the US industry, and I'm really glad to be here and talk about it. Thank you.
I'm Melissa Hertel. I'm a naval architect with Crowley Engineering Services, and our study was to do a technical validation of a US feeder to support installation, and Crowley Maritime owns and operates a lot of vessels. So.
Well, thank you all for taking time out of your week. I know you're all extremely busy, and we're all really looking forward to hearing your presentations. But just to set the scene a little bit so we can contextualize the offshore wind supply chain, and Ross is going to probably dive a lot deeper into this than I will. We're all aware, and it was emphasized this earlier in the last session, that the US offshore wind industry has really ambitious goals. And the industry right now is extremely dynamic, it's very fast-paced, and probably arguably represents the geography with the largest investment dollars for the offshore wind industry worldwide. Announcements on state procurement, funding for ports, new lease area auctions, supply chain investments, programs for workforce training happen on almost a weekly, if not a daily basis. So as a result, any attempt to get that baseline of the future demand needs is very complex and represents a very complex challenge to solve. And to provide some context on what the 30 gigawatts by 2030 goal might mean, depending on which turbine size you choose, it could be anything up to 2,000 turbines and foundations. We're talking 4,500, 5,000 blades, multiple thousands of kilometers of cables, and the potential come 2025, 26 to have 10 commercial scale offshore wind projects being installed concurrently. Now that puts pressure on port spaces and vessels, and just emphasizes the level of demand that will require a complex domestic supply chain, and certainly some clever and innovation to make that happen. And thankful that the NOWRDC is supporting all these projects to support that innovation. And this is before we talk about floating wind in some of the, certainly and obviously in California, but even now, just last month, the Central Atlantic lease sites that were identified as by some distance the deepest floating wind sites in the world. So the rise of a domestic supply chain will bring a number of advantages, you know, enabling current suppliers to get involved in the industry, thousands of jobs, and the potential that the United States can become a net exporter for this industry into the future. But you know, these advantages will only be recognized through significant domestic expansion in manufacturing, infrastructure, and workforce, all of which today are currently insufficient to support commercial offshore wind projects. That being said, and again, I'm sure Ross will allude to this more, that there's significant moves afoot, and we've already seen significant commitment from Tier 1s and Tier 2s to support the industry. We've seen commitments at the Port of New Jersey. We've seen multiple tower manufacturing in Albany, foundations in New Jersey and Sparrows Point, secondary steel in Rhode Island, Connecticut, New York, and we continue to see Tier 1s plant their flags as funding and incentives come together through the OREC and PPA solicitations in New York that's coming up, but following that, New Jersey, Rhode Island, and Massachusetts. So watch this space. It's, like I said, a very fast-moving industry. Before I hand over the presenters, I just want to say one last thing, and Congressman Kennedy touched on this, is the impact, both positive and negative, we could have on marginalized communities, including environmental justice communities, low-income communities, communities of color. Many states now consider equity as an important pillar of their energy policy, and we, as an offshore wind industry, have a unique opportunity as we build this industry to positively drive and affect that change. And I would encourage everyone to read a report released by the Clean Energy State Alliance just last month that dives a lot more detail into that. So with that, I'll hand over to Ross of the Business Network, who's going to give us an overview of the 30 gigawatts by 2030 supply chain roadmap. And just a reminder, there's the Slido code again for questions as they come in. Thanks.
Thanks, Jeremy. What's advancing here?
Just
the
yep,
arrow key.
that
That's
works.
simple. All right. Thank you, Jamie. As I said, it's a pleasure to be here with all of you all today. Thank you, National Offshore Wind Research and Development Consortium. I also want to particularly thank Christine Sloan, project manager. Thank you for your last 2 years of partnership on that project. Also want to thank Matt Shields, project manager from our project co-partners, NREL, the National Renewable Energy Laboratory. Matt, thank you. Appreciate your partnership over these last few years on the project. So, great. So the supply chain, what is the supply chain? Well, it's pretty simple. It's basically all the parts, all the pieces, all the services, and all the people required over the life cycle of an offshore wind project. We're talking about all the sub-assemblies and sub-components that go into blades, turbines, foundations, floating platforms, sub-assemblies such as mooring systems and the components of the mooring systems, anchors and chains. In our work, we focused on the products of the supply chain, the manufactured and fabricated parts and pieces of the supporting infrastructure of supply chain, the vessels, the ports, and the people that provide the services to bring the wind farm to life. And I'm not just talking about the engineers. I'm not just talking about the lawyers, the financial people, and the permitting people. We're talking about the crafts. The people with the craft skills, people that are assembling and manufacturing the components. Again, my name is Ross Gould, Vice President for Supply Chain Development for the Business Network for Offshore Wind. And as I said, it's my pleasure to be able to talk on behalf of the project team about 30 gigawatts by 2030, a supply chain roadmap, an actual very unique and novel look at the supply chain here in the United States. Now, the Business Network tracks. The Business Network is singularly focused on offshore wind and growing its supply chain, and we focus on education, collaboration, and innovation. The Business Network tracks the market on a 24/7, 365-day year. 65-day year frame, and we put that information into 2 digital tools, one of which we used for this project. It's our Supply Chain Connect database, which is the premier national offshore wind supplier registry here in the U.S. We have data on over 2,800 organizations right, that have stated their interest, right? They're interested in joining the industry, and also their capabilities and experience. It tracks things such as manufacturing facilities locations, the certifications, the size of the workforce, experience on US-based or international-based offshore wind projects. We also track, we also have a market dashboard in which we maintain market intelligence. That is where we maintain our up-to-date information on project status, where the project is in its life cycle, and also maintain all the supplier contracts. Who's got contracts with what project, and that's things such as engineering services, geotechnical studies are in there, and also people that are supplying the secondary steel handrails for platforms and transition pieces. So, as I said, we're membership 550 growing. In 2019, industry leaders identified supply chain as the #1 concern, and they seeded the idea for a supply chain roadmap to understand what is actually required, right? What's the demand? How many components, how many products, how many ports, how many vessels are required in order to build out the 30 gigawatts by 2030? And so the Business Network teamed with the National Renewable Energy Laboratory and DNV. And this team, we fleshed out a more detailed study, and we were able to secure some funding from, and I want to thank the Department of Energy, National Offshore Wind Research and Development Consortium, Maryland Energy Administration, and NYSERDA, New York State Energy Research and Development Authority, for that funding. So the goals are to provide basically an understanding of our existing manufacturing capabilities, overlaid on a likely demand pipeline. What does it look like? What is our deployment of the 30 gigawatts going to look like? When is that happening? In what years? The novel study is looking at not only what is needed in terms of the number of major manufacturing facilities. You heard Jamie talk about the turbine facilities, the blade facilities, the tower facilities that are already announced that they're setting up, but we also looked at the existing tier 2 and tier 3 suppliers, those people that supply, those businesses that supply the sub-assemblies and subcomponents of the industry. So that's the novel piece, one of the novel pieces here with that. And we also wanted to take a look at what is really needed in terms of tier 2 and tier 3 engagement. And then one last point is that the team aims to provide several scenarios for building out a domestic supply chain and to consider impacts on project costs and regional economic benefits. And really, what this study is going to highlight is it's going to be highlighting the opportunity cost, the opportunity space for suppliers in offshore wind. Here's just a slide on the work we've performed, but in a nutshell, we collected data on project deployment schedules, on announced large component manufacturing facilities, on vessels, on ports, and on existing manufacturing companies, and performed scenarios to envision what the requirements would be for a fully domestic supply chain. In March, we published the Phase 1 report that provided scenarios for the demand side of the equation. And I realize there's a lot packed in on this slide, but stay with me. I'll point out the things that are really worth hearing about. First, here on the left-hand side, on your left up here, in the demand for offshore energy, wind energy. The demand for a domestic offshore wind energy supply chain report, we highlighted, as you had heard from Jamie, that there's a need for 2,100 turbines to reach the 30 gigawatt goal. There is, same for foundations, right? 6,300 blades, and a need, and Jamie, I'm going to put it into miles like we do here in America. It's the 7,100 miles of cable. And at a peak, and this is really important, and we'll be getting into this later with the feeder solution discussion, but at a peak, we're going to need 5 to 6 wind turbine installation vessels, and also up to 49,000 workers to get us to the 30 gigawatts. Now, the Phase 1 report, it also highlighted, as you move on to a little bit to the right-hand side, the supply chain depth, there's a cascading impact here of the supply chain, right? It's great to have a blade facility. It's great to have a turbine facility, but the tier 2, tier 3, the subassembly and subcomponents, that is really where the bulk of your supply chain revenues are, as well as workforce will be. So
and when we're talking about those subcomponents, we're talking about gears, switch gear, fabricated steel, and components of that nature. As we move on, just to one more slide over here to the, actually go down for a second, to further flesh out this idea of cascading tier 2 subassemblies, an offshore wind substation, it has 92 subassembly and subcomponents, the top side, telecommunications, auxiliary equipment, and foundation. So there's that cascading effect, right? The main tier 1s are built, they're assembling all those 92 components. And then just want to point out that in the breakdown of direct versus indirect job creation, more on the right-hand side of the slide there, the study also took a unique look at how many jobs would come from different manufacturing facilities as they announced along the major components from nacelle and blade, and it did a comparison of the direct and indirect jobs that come from siting those facilities. Now, as two of my fellow panelists perform projects on feedering, I wanted to highlight that the project team looked at and highlighted wind turbine installation vessels as an area of great risk to meeting 30 gigawatts of 2030. I know we've heard a lot of that anecdotally, and I think that's actually a good point to raise here, is that a lot of the information that many of you in this room that have been veterans of the industry have known anecdotally has been confirmed by this report. So I think that's a very important piece to note. So we're going to, the vessels is at risk. We need 5 to 6 of them at our peak for peak installations. In the next phase of the study, we switched. The first phase was about the demand, how many turbines, how many gears, how many switch gears, how many blades. Now we're looking at the supply side. How many existing manufacturers do we have? How much can they provide? We looked at the project team reviewed the domestic manufacturers and assemblers and fabricators of steel structures that identified them through, as I mentioned earlier, the Supply Chain Connect registry. The team looked at experience in offshore wind and adjacent industries, locations, certifications, size of workforce, and a number of other factors to make assessments of capabilities. We developed a metric to analyze the data, and it's called the Adjacent Industry Manufacturing Scale, which tells us what a state's existing manufacturing base could contribute to the offshore wind industry based on certain scenarios we ran. Again, I just want to say that this is all, a caveat here. This is based on specific scenarios. So if your state is seeing a color that you are not sure that you disagree with, first, I'd like to have a conversation as we flesh out our report. But secondly, just understand it's under specific scenarios. And then the team is. Oh. Is that for me? So the team also identified a number of barriers to supply chain growth. I'll quickly mention uncertainty surrounding development pipeline, which creates risk in investment. That uncertainty, a lot of people think of it only in terms of project developers and it being project developers or the OEMs won't invest. Well, that's not only true. Labor unions also may not invest if they see uncertainty in the pipeline, and they won't invest in their training facilities. Other academic institutions may not invest in developing curriculum because it's an uncertain investment, because of the risk they see. So certainty has a major impact on this on the supply chain, up and down the supply chain. And then current supplier networks are stressed. Are another barrier we're going to be facing. Everyone is constantly hearing about supply chain issues these days. We'll probably hear a bunch more supply chain issues as we go into the holiday season and all try to buy our presents. And then another major piece is that existing port and vessel infrastructure is currently inadequate to meet our 30 gigawatts. So what can you expect to see in the roadmap, which we'll be publishing in January? We'll summarize these major barriers that I had just gotten into, and we'll provide a lot more detail and information and discussion around those barriers. We'll describe the major factors that need to be considered to develop a resilient and equitable manufacturing capabilities, one that looks to communities that have been left out of energy development in the past. And then also we'll present a scenario for domestic supply chains that estimate the numbers of required manufacturing facilities. So you're gonna hear, and you'll have to stay tuned for our final report, but we're gonna have a projection for the number of major manufacturing facilities that we would require domestically to have a fully 100% domestic supply chain. And this is just a summary of those next steps, but most importantly to all of you, and I hope it's important to all of you, and you will take a look in January when we publish our final supply chain roadmap. So with that, thank you. I appreciate the time, and again, I appreciate the National Offshore Wind Research Development Consortium for the invitation to be here today to talk about our work. So thank you. I look forward to your questions.
Thank you, Ross. I'm going to hand over to Pat Taylor now.
Hi, thank you, Jamie. Thanks for having me. My name is Pat Taylor. I'm a technical program manager at Anduril Industries in our maritime department. I'll be speaking to our NOWRDC project that we were awarded for fully autonomous subsea asset inspection using an autonomous underwater vehicle, or what I'll refer to as an AUV for this presentation. I just want to thank Julian and Corey from NOWRDC. They've been extremely useful and helpful, and a pleasure to work with. And anyone out there that has worked with them in the past, I'm sure would echo the same sentiment. So they're truly the secret sauce of why the consortium has been so successful thus far. And I think it's important to give credit where it's due. So thanks, Julian. So I'll give a brief overview of our Dive LD platform, which is the AUV that's commercially available from our company. I'll touch on the project that we were awarded with NOWRDC. Then I'll give an overview of the offshore wind specific product that we're developing. And my final topic I'll touch on is the autonomy and algorithm development that is part of the project that we've been funded for. So, like I said, I'm Pat Taylor. Matt DiPietro is our business development lead for commercial. So maybe some of you have met Matt. And Eric is our lead engineer on this project, who's been in the industry for decades. So the Dive LD platform is an autonomous underwater vehicle. It's not tethered to a surface vessel, so it is totally there's no human in the loop when we deploy these. It's 19 feet long by 4 feet in diameter. It is capable of going to full ocean depth, which is about 6,000 meters. So it's great for like an offshore wind floating platform survey set, which is going to be a challenge to survey, as many of you are aware. We can survey for about 4 days continuously, or if we're not surveying, we can transit for about 10 days. So if you think a few days transit, a few days survey, it's somewhere in between 4 to 10 days of time it can be out on the water. And we do have best-in-class navigational accuracy on the vehicle. So for instance, if the vehicle traveled 100 kilometers, it would be within about 20 meters of its anticipated location, which is pretty remarkable. So the project that we were awarded through NOWRDC focuses on asset inspection. I do want to point out before I jump into it that AUVs have a great, they're able to be used across the whole life cycle of the wind development life cycle, right? So there are lots of different use cases. You could use the surveys when developing your SAPs, your site assessment plans. During the construction plans, lots of survey work can be done by the AUVs, and all the way through operations and maintenance. So I'll focus on the operation and maintenance phase of the life cycle just because that's what the award for the project was. But keep in mind that there's many other use cases for AUVs that I think can really help bend the cost curve of the infrastructure. So as many of you know, BOEM necessitates frequent asset inspections of power transmission cables, scour protection, other infrastructure involved with offshore wind farms, right? So our proposed solution is to use an autonomous underwater vehicle, an AUV, to peer launch and conduct asset inspections of those buried cables and check burial depth or other anomalies that our advisory board will tell us is important to note. And then with our partner Metron, we're developing an algorithm to detect anomalies in that cable on the edge in real time on the vehicle. So no human in the loop there. the data will stream from whatever sensor we're taking on. The algorithm will identify an anomaly on that cable, and then the advanced autonomy solution that we're developing as part of the project will retask the vehicle to go take a second look at that anomaly and do something dependent on what the use case, the mission set is. So for the demonstration at the end of the 12-month project, we will be conducting a survey on the power transmission cable that runs from Point Judith to Block Island off the coast of Rhode Island. And yeah. For our timeline, we did just kick off, so we are looking for our project advisory board members. So if any of you in the audience are interested, please let myself or Julian know. We'd be happy to have you on the team. So we'll kick off here shortly. In the first 3 months, we'll develop our system design report. We'll be down selecting on our trade studies for sensors and defining the algorithm architecture that we're going to use, depending on what sensor set it is, likely to be a sub-bottom profiler scan of that buried cable. At the 6-month mark, we'll do our integration report where we will do bench testing and initial training of our algorithm, and then we will start our checkout of the integration. At the 9-month mark, we'll be doing initial in-water testing pier side and additional algorithm training. It takes a lot of data to train an algorithm. And then we'll commence the final phase, which is the at-sea demonstration at the 12-month mark. So how are we going to execute this project? So we are going to equip our vehicle, which we've already started, with a side scan sonar, a sub-bottom profiler, a multi-beam echo sounder, and a optical camera, probably going to use the Voyas camera. And on the top right there, you can see our concept for a sub-bottom profiler algorithm. Automatic target recognition algorithm was what we're calling it. So you can see a representative hyperbola of a sub-bottom scan of a cable, and we are proposing that our algorithm would identify that cable and determine its burial depth or if there's an anomaly associated with that cable. The algorithm will then identify that burial anomaly, maybe it's surface, maybe there's something else going on, and then the vehicle will retask itself to update its survey plan with for a side scan or optical imagery capture of that certain portion of the cable, and then we'll report back to the survey team or the developer, whoever has hired us to do this mission. And then, like I said, this is an overview of the vehicle itself. We've tailored this specific vehicle for offshore wind specific surveying. So, multi-beam, side scan, sub-bottom, likely to have a magnetometer on there, self-compensating magnetometer, and then an optical camera. And we are actively integrating these as we speak now, so we're a little ahead of our timeline. And then I just wanted to amplify the algorithm development that we're having. So this algorithm already exists in our toolbox. So on the screen you can see it's a MinSAS, but it's post-processed data that our computer vision and machine learning algorithm has identified a cable and the mattressing associated to it. It's also identified a lobster pot to a fairly high certainty. So as part of the project, we'll be taking this algorithm and putting it onto the vehicle and processing in real time without any human in the loop. So that's a pretty big step for us. And then additionally, we'll be upgrading our advanced mission autonomy. So on the right there, you can see the vehicle will automatically plan its survey routes, take in current weather conditions, and it will retask the vehicle to do a secondary scan of that anomaly that the algorithm has identified, depending on what we're trying to look for. And that's all I have. Thank you.
Thanks, Pat. Really interesting piece of kit there, and I think it speaks to Walt's information in the keynote about moving towards a more autonomous kind of industry. So that's great to see. Next up, we have Melissa Hurtle from Crowley. Thanks, Melissa.
Hello. I'm going to talk about a project that we did on validating existing U.S. flag with minimal modification. And I want to thank Jürgen. He was our original project manager, and Mel Schultz is our current project manager, and they've been great help to us. Also, just as where we are in the project, we've submitted all of our milestone papers, including our final, but it's in draft state, so we'd be interested in any comments if anybody has any. Okay, so the purpose of the study was to validate by analysis and simulation that a minimally modified deck cargo barge can, accompanied by the appropriate tugs, will be a cost-efficient and expedient way to install wind turbines. And so we looked at, a lot of these things have been looked at sort of piecemeal, but this is looking at the whole thing all the way through. So we did dynamic motions analysis, we did a maneuvering simulation, and then today what I'm going to talk about is the feeder weather downtime study, which incorporates everything from the rest of the study. So weather downtime analysis, the tool we have is a single agent, so it models either the feeder or the installation vessel, but there's no way currently to put those two things together. So you model one, when they're interacting, those have the exact same task lists and weather requirements and all that, and that's how we're sure on every route that they could be in the same place, but they're not necessarily, which is one of our things we're going to look at for future improvement. But what this does do is it starts the simulation at every hour for 31 years. So we get a huge sample of runs, so we can do statistics on it, and so we can both monthly and annually, and to have a pretty good, very good level of confidence. So so what we're looking at today is the P50 confidence level, which is sort of an average year or what you can expect over a long period of time. And then we're looking at the P90, which is kind of a really bad year, and hopefully not what we do over a long period of time. Hopefully it's just a bad year. And so these are the things we looked at in our study. So generally when you do a weather downtime study, you're just looking at weather. In this case, we are looking at cargo accelerations for each piece of the cargo, because the OEMs have a limit for accelerations. We're looking at feeder, bow, and stern lateral velocity, so when it's coming up near the WIV, it's not going so fast it's going to crash into it. We look at wind speed and direction, and we can actually take those two things apart. So maybe you can have like when the barge comes up to the installation vessel, if the wind is from the side, we can only handle 20 knots, but if it's coming from the bow, we can handle 25 knots. So we've taken that kind of directionality into account. Feeder roll and pitch angle, which is important when you're trying to discharge cargo, because that can, you can have rehits and that kind of thing. And the cargo top and base motions while you're lifting, because obviously if it's moving too much, you can't really lift it. And then we looked at 8, down the right-hand corner, it talks about the 8 conditions that we looked at, which we looked at 2 and 3 tower sections. Obviously, it's easier for us to transport 3 and offload, but 2 is faster, so we looked at both. And we looked at sort of the Marine Warranty Survey ballast condition, which is a pretty heavily ballasted, and we also looked at a very light ballast condition to see if that made a big difference. And then we looked at everything was both full and empty, and then actually for our simulation, we also looked at just the towers removed. So the motions pretty much change a lot when you remove those towers. Here's a kind of a quick look at the how we did the limits. So on the right, you can see there's a big long list of limits, and we grouped them together and put them in the smaller limits on the left. So, for example, when you're transporting the cargo from the load port out to the site, you're interested in accelerations of the cargo in X, Y, and Z directions, and there's either 5 or 6 pieces of cargo, or 4 or 5 pieces of cargo. So those all feed together, and like this, that approach to the WIV, that's probably the most limiting, because your cargo acceleration can't be too high. The barge has to move slowly next to it. You can't have top motions too much, or you might hit something. But anyway, each step of the round trip voyage uses all of these. So we had 22 limits and 75 sublimits, and so we're wrapping that into the overall simulation. This is an example of just one. This is just accelerations and motions for the top, for Tower 3. And what we did was we used SRAOs to get the motions, and then you could put that with the significant wave height at that exact moment to get the motions at that moment. And then here is our route planning. We did 2 routes. We did our long route, which is Salem to Empire Wind. Our Crowley's load port is in Salem. And then we did a short one, which is Brooklyn to Empire Wind. So the one is almost 400 nautical miles, and the other one's at only 80. So it kind of gives you a good range between how a long route and a short route matter. And the other thing this does for us is it gives us a heading. So for example, when the barge is coming into the lower right-hand corner, when you're between the midpoint and the lower right-hand corner, you're on that heading. And then when you turn west, you're on a different heading. So when we're headed south, if the weather is coming, or the swell is coming from the bow, there's less motions, whereas when we turn to the west, the swell might still be coming from the south, but there'd be more motions. So directionality is important. And here's a list of the feeder tasks that have to be accomplished, and they're roughly grouped into those bigger categories. A round trip, so we looked at what we call a multiple barge system, which is a M system, which is what I'm showing here. But if you have a single barge, then the barge has to wait to be loaded. If you have a multiple barge, one barge can be loaded while the other barge is off delivering. And the difference there is 17% in time. So with no weather downtime, an M feeder system can make a round trip between Salem and Empire in 4.8 days. That's ideal, but it's no weather. And so that would mean they could deliver 75 turbines a year. And it can make a round trip between Brooklyn and Empire in about 1.6 days. So it could deliver 225 a year. But again, that's no weather. So that's kind of a benchmark. And then here is what the installation vessel can do. And with no weather downtime, it can complete an installation cycle where it approaches the site, jacks down, has the feeder come alongside it, takes the cargo, and puts it on lets the feeder go, and finishes its installation and moves to the next site in 2.1 days. So it in theory could do 177 a year with no weather downtime. And then we also compared it to a Jones Act installation vessel that could transport 4 turbines at a time. So it would make a round trip between Salem and Empire in 11.8 days, or between Brooklyn and Empire in about 9.2 days. So it could deliver either 124 or 158 a year in ideal situation. So here's the interesting part, which is why I went so fast through the first part. This shows the seasonality of the installation vessel. So what's on the left is the multiple, the barge, the feeder vessel. The blue is the single vessel, and the red, or the orange dot, is the multiple. And so the single vessel, the dark blue is the P90 and the lighter blue is the P50. So you can see this is how many days per weathered wind turbine it takes to do that on a round trip basis. So you can see in the, for example, at a P90 level, which again is a really bad weather year, it takes 3.3 days in June, which is 60% longer than no weather. But in February, it takes 6.5 days, which is 3.2 times as long as no weather. And then on the right is what the installation vessel can do. So you can see the difference between the darker gray dot and the light gray dot. That's the difference between P90 and P50. So you can still see it very seasonal in the winter, there's a big difference between the two, and in the summer, there's not very much difference. But this way you can see, you know, is it worth it to spend 10 days in January to install or to transport? And it might be. But when contracts are written, you know, people might want to pay attention to, you know, it's going to be a lot more in the winter, but you still get some installed, that sort of thing. But and this also can help you determine what the value of a piece of equipment that might help improve your utilization might be worth. Because if you can cut down 3 days of a piece of equipment that costs $250,000 a day, that tells you how much you can pay for that piece of equipment. So that's just this is just the baseline case, though. This is what you can do with kind of our standard limits. So here's comparing a Jones Act installation vessel that's going and picking up its own cargo to a feeder supported, so there'd be a foreign installation vessel supported by a U.S. flag feeder. And so we've put some kind of base prices here. So we're saying a foreign installation vessel is 1 times X is the cost of it. And we're saying a foreign installation vessel with a feeder with 1 barge and 2 tugs is 1.3, and with a lead and assist and 2 barges is 1.4 times X. So again, these are, who knows what the price is going to be, but this is just a benchmark we put in place. So for the Salem to Empire route, an installation target of 60 turbines a year, the installation vessel with 2 barges, the Jones Act day rate, if it's greater than 1.13 times the price of the foreign, it's more expensive than the Jones Act supported foreign installation vessel. And then for Brooklyn to Empire with a target of 25, the 1.19 times the day rate would be for that size. But everything changes when you change your number of installations or your number of turbines you're trying to install, because of course it's most expensive in the winter. So if you can do the 65 in better weather, you're getting them done in fewer days per installation. So, so one other thing that we did quite a few of these sensitivities in the study, but I'm only going to show one here. This is how sensitive is the system to top and base motion limits. So this would be, for example, if you wanted to use a motion compensation system, how much is it going to save you? So what we looked at here is 1 meter, 2 meters, and 3 meters of top and base motion. So if you can see the 1 meter is the green line, where it's the highest number of days per installation. So the green solid is the P90 and the dashed green is the P50. So probably for writing a contract, you know, it's hard. Probably the best way to do it would be to do it based on P50, but the person installing it's going to probably be basing their costs on P90, because you never know what the year is going to be. But at any rate, what this shows is if you have a piece of equipment that can cut your top base motions from 2.5 meters to 1.5 meters, that cuts the installation cost only by 5% in a bad weather year, but 11% in an average year. And if you have a system that reduces the motions from 2.5 meters to 1 meter, it'll cut the installation cost by 30% in a P90 year or 21% in a P50 year. So this can kind of give you a way to price out what those motion compensation piece of equipment be worth. And then you can see over to the one on the left, it says how many days per turbine to install. And when your base top motion limit is down by 1 meter, you're up over with the orange dot there, the P90 with the multiple barge, you're at 10 days, or just under about 7.5 with the P50 with the 1 meter. And then when you get out to 3, even over 2.5 meters, you're hitting an asymptote. So 2.5 meters or so, you've dropped down to like a little over 8. So some of the other things we looked at was, like I said, the different load conditions. How does that change your deliverability? How does your velocity of coming alongside the installation vessel, how does that change your installation, how many you can install? We looked at, well, we looked at a lot of things, anyway. But anyway, that's my presentation, so.
Thanks, Melissa. I think the Jones Act is something very unique to the US. So seeing people dive deep onto these topics is great to see. And I think we're going to hear now from Atheendra Sreenivasan, who is diving even deeper into this topic again. Thanks.
Thank you, thank you, Jamie, and thank you, NOWRDC, and Julian, Mel, Corey, and of course, blanked out on your name, Jürgen. Sorry, I say, sorry. Yeah, we worked with Jürgen last year. Our project mainly lasted only last year, so we mostly worked with Jürgen. Also, it's very nice to be here, and it's great to see the Boston weather is also cooperating. I came up from Houston, and I was not looking forward to spending a week in the cold, and at least it's not super cold. My name is Atheendra, and after Melissa, I'm also going to talk a little bit about floating feeder solutions. Our project was a little more focused, but we did a little more detailed calculations on just the lifting aspect of components from a floating feeder vessel. And the title of our project is Comparative Operability of Floating Feeder Solutions, and it was funded, it's the NOWRDC Project 107. We started it last year, and early this summer we have already completed the project. So if you can go to the website, you can already see the final project report there if you want to take a look at it. In my short time, 10 minutes here, I will just quickly go through some of the main aspects of the project team background, why we did this, and some project methodologies and the main results. To put some names and faces into the project team, the main contractor for this project was MARIN. That's the Maritime Research Institute, Netherlands. We are a hydrodynamics institute based in Wageningen, and Ariane was the lead of the project, and I did all the simulations. We both work in Houston. Joritian was our colleague who gave support from our Dutch office. The peer review and methodology was given by American Bureau of Shipping, and Wei Huang and Xiu Wang were our contacts at ABS. And St. James Marine is an independent consultancy based in Atlanta, and Michael St. James is a mariner with 40 years of experience and 12 years in the offshore wind industry. And he was instrumental in bringing together a lot of stakeholder companies for this project, and he provided project coordination and interface management. And these were all the list of stakeholder companies for this project, and as you can see, they represent a wide range of the industry, whether it's developers, EPCI contractors, feeder, barge operators, naval architects, and they provided a lot of input, and we had regular meetings with them where we understood their version of the feedering process. And since there were also a lot of competitors, we signed NDAs with all of them, and all the data that we used were kind of averaged between all the data set we received, so we didn't use any particular data of a company. And I think in this crowd you're already aware, we listened to this a few times today already. The 30 gigawatts by 2030 is very ambitious, especially because the US currently doesn't have the vessels to do this. Traditionally in Europe, you had jack-up installation vessels that loaded maybe 4 or 5 turbine components. from the port and went offshore, installed it, and after a month maybe came back to port, loaded it again. Right now the 30 gigawatt target translates to about 2,000 wind turbines. And as Ross already and Melissa mentioned, that would probably need about 4 to 5 installation vessels operating right now. And complicating this a little more is, of course, Jones Act, which means that European or foreign vessels cannot call on US ports. There is one Jones Act compliant vessel, Charybdis, that's being built down in Texas, but it'll go into operation only in late 2023 or early 2024, and it's already forward contracted, I think, till the end of the decade. But one vessel won't be enough. So in the next near to mid-term, necessarily we will have to look into the feedering option unless somebody comes up with a totally different installation methodology. So in this context, feeders are ships or barges that will be used to transport components from a US port offshore to the offshore wind farm location, where European or some other foreign installation vessel can lift up these components and then install it. So this was the reason we started the study. We wanted to understand the risks involved with this feedering concept, and also we wanted it to be kind of like an independent assessment since we there are a few different feeder designs available and a lot of heave-based or deck-based compensation tools available. We wanted to kind of give like an overview of what is the effectiveness of all of that. And also this operation, there are 2,000 turbines, maybe 4 lifts per turbine, so 8,000 lifts that has to happen to install these 30 gigawatts. These feeder operations have taken place in the offshore oil and gas market to install topsides of oil platforms, but these are generally one-off operations, and you can wait on a good weather window before taking these topsides out and using crane vessels to install them. But if we want to do this for the offshore wind market, where you need some availability through the year, we need to look at into a little more detailed on what we are dealing with and what tools will help us increase the uptime. So what is the background of the crowd here? Like, are any of you naval architects or offshore engineers, or what? I see some hands going up. Okay, I'll try not to bore you too much. I will just give a very quick overview of what we did. We used computer simulations to look at this problem and quantify what is the uptime of different feeder solutions. Used a combination of time domain and frequency domain analysis. So time domain is effective because when you lift a component of a feeder vessel, the draft of the feeder changes, the roll period changes, there is a lot of other nonlinearities that are happening. And then once we had a handle of like what is the limits at which these lifts can happen, we used frequency domain analysis to look at a wide range of solutions. So this was like the averaged feeder we looked at. So there are a lot of designs out there for purpose-built feeder vessels for the US market. None of them are built, and they will probably all take 2-3 years to build. So this won't be the go-to option right now. The go-to option would be some existing barge, but this was a 100-meter long ship that we used for the analysis, and it carries a 115 megawatt turbine. The tower is in 2 pieces. There's a nacelle, and you can see the blades set, and the blades are about 120 meters long for a 15 megawatt turbine. And you can see the support structures are about 70 meters apart. Just keep that in mind. I will come back to that a little later on. And we didn't model the jackup vessel itself. It is fixed to the earth, so we considered it's not moving a lot. And then we ran simulations of all the different lifts. So the current generation of jackup installation vessels, their main crane has capacity of about 1,600 tons. And these cranes can lift at speeds of about 10 meters per minute. And we also did all these lifts with and without heave compensation. So heave compensation, denoted by a small block in the picture there, it can prevent snap loading on the crane line, so it kind of helps reduce the loads. And we did these simulations in a range of wave heights, peak periods, directions. I'll see if this video plays. I think this was a PDF file, right? So, okay, I guess the video doesn't play. Anyways, this was supposed to be a lift of a nacelle. And what happened in this lift was we had 1.5 meter waves at 10 seconds from beam on to the vessel. And when the lift was happening, so this heave compensation device also has something called a quick lift functionality. So it can lift at a much faster rate of 24 meters per minute, but it's limited to a stroke of 2 meters. So while the main crane itself is very slow, this heave compensation can lift it up very fast so that when you're lifting it, the vessel doesn't hit the component again. And in this particular video, it showed that when the nacelle was being lifted. And one more thing to note is when you lift a heavy component of a vessel, it changes the roll period of the vessel. So once you lift it, it is possible that the wave can kind of resonate the roll motions, and suddenly the roll motion of the vessel can increase, and rehits can happen. So we analyzed all these simulations, and we looked at component accelerations, crane line tensions, and rehits. Rehits, as I said, is when you lift a component up and then the vessel impacts it again. And generally OEMs don't, there is no such thing as a soft rehit, like you don't really want any rehit at all. And because most of the failures that we saw were dominated by rehits, we were able to kind of derive a relation between the heave motion of the vessel at the base of the components and how often the rehits happen. And you can see like this, these lines kind of increase as you go to the right. So as the base heave motion of the vessel increases, then it's also more, there are more chances that the components will have a rehit. And rehits were most common for the blades. And I told you in the beginning that the blade support structures were 70 meters apart. So you can kind of imagine that when you lift the blade up, it's almost the whole length of the ship. The vessel might be pitching, and when you lift the blade up, it's possible that one of the support structure gets impacted. And there are companies looking at, so instead of putting support structures at two ends, you can kind of also have a central support structure. So that kind of prevents this problem a little bit. So what we found from these simulations was without heave compensation, we could handle up to 0.1 meter heave RMS motions. And with heave compensation in the crane, that increased quite a bit to, the limit increased to 0.4 meter heave RMS that was acceptable. So now that we had these heave limits, we looked at a bunch of different variations. We looked at 3 different feeder vessels. One was the original 100-meter long feeder, one was a 120-meter long barge, and one was a 160-meter long feeder. The larger feeder, we just looked at it because one of the members of our advisory committee wanted us to let people know, like, just as out of curiosity, what it would look like if you have a much bigger vessel there. Currently, there are no such feeders available, so that feeder is not available, but it's good, instructive to see how it performs. So there, and we looked at anti-roll devices. Essentially, we increased the roll damping in our model to kind of simulate anti-roll behavior, and we looked at some skidding systems. So if you have rails on deck, so that you can transfer the components from the side to the center line before lifting up, you could possibly decrease the motions a little bit. We wanted to look at its effect. And then in addition to compensation systems on the crane, there are also compensation systems on the deck. And we looked at that too, and based on the assumptions we had made in the study, we found that the deck-based compensation system had a similar effect to crane-based compensation system. And finally, we took 3 years of wave data from Massachusetts, and you can see here most of the waves come from the south. And the waves mostly are around 1 to 2 meters in HS, although you can also find much higher wave heights. And the wave peak periods range from 6 to 10 seconds. And on the bottom right, you can see like a time trace of the wave heights. And you can see that in the winter, the waves are quite a bit higher than in the summer. And so this table has a lot of numbers and a lot of colors. So I don't know how much you can read from there, but reddish colors are not good, green is good. So what this says is this gives the uptime without any motion compensation. And we looked at feeder vessels heading south. So the feeder vessel is heading into the waves. And we assume it takes about 16 hours for the whole operation to complete. So you have 4 lifts. Each lift takes about 4 hours. And you can see there is the 100-meter feeder, barge-shaped feeder, 165-meter feeder. And the total uptime is quite low. For the 100-meter and 120-meter feeder, the total annual uptime is only 10%, which is very low. But this is without any sort of compensation system. And in the summer months where the waves are lower, you have up to 30% uptime. What the 30% means is during 30% of the days in any given month, we have a 16-hour window where we can do all the 4 lifts one after the other. So when you go to the much bigger feeder, the total uptime does go up from 10% to 30%, and that also shows up in the summer months where it's significantly higher. Now, when you look at uptime with motion compensation, either based on the crane or on the deck, now the numbers are quite a bit better. Now you have, with the smaller vessels, you have 50 to 60% uptime, annual uptime. In the summer months, they are up to 90%. With the bigger vessel, it's the annual uptime is 80%, and in the summer, it's almost 100%. And one more thing to note here is in this particular table, having rails or roll compensation devices doesn't seem to give a lot of advantage. But we didn't look at the tower top motions, which is where these systems can have a huge effect. So when we started the simulations, we assumed the lines were already connected to the components, but the connection itself will be very tricky. And it is there that deck-based compensation systems or roll devices can play a big role. So I hope I haven't run too much over my time. This is the final 2 slides. So this is the main summary of our findings. So the blades, so we did the computer simulations of a bunch of different feeder vessels. And the downtime in this model was mainly driven by the blades, mainly because the support structure of the blades are very wide. And that can be mitigated by having a central support structures. It is crucial to look at the feeder motions before and after each lift, because the characteristics of the vessel motions can change a lot when you lift something up. The uptime is very minimal without any sort of compensation system. So you need either a crane-based or a deck-based compensation system. And uptime is strongly seasonal. It's quite higher in the summer months. And we also identified a bunch of other challenges. So our project was quite short. It was only 9 months. So as you can see in the final box, that we did a comparative study where we tried to compare different feeder vessels and solutions, but it was not a comprehensive operability study. So there are all these things that are worthy of subsequent studies or are very important for. The first one is feeder station keeping. So you can, when you tow out all these ships to the offshore location, you can either have a DP system that keeps position, or you can have tugs that hold these feeders, or people are also considering mooring the feeders to the jackup vessels. So in all these cases, they come with their own risks. A DP system might perform best. Mooring it to the jackup, you will have to do further studies on what the impact loads has on the jackup legs. The component horizontal motions are also quite crucial. You can have tugger lines that kind of control when you're lifting a 80-meter tall tower. You can imagine that even a small penduluming motion, it can get quite unsafe for anybody on deck. So you do have to control that. And then you have a release of sea fastening. It's very easy for us to simulate whatever we want in a computer, but when you have people working here day in and day out, and you have to lift a component, and you have sea fastening there, you have to first release the sea fastening and then lift the component up. So there is a lot of nuance that goes in there, and a lot of different companies developing automated sea fastening tools that can act there. But mostly the main takeaway, if you will, is this will be a very difficult operation with a lot of moving parts. You have the lifting supervisor on the installation vessel, you have the crane operator, and then you have the deck compensation system operator or the sea fastening operation system operator, and they all have to be on the same page. So training is very important, and also they need to be sure of how they are all communicating with each other. So hopefully, yeah, the human factors and training, that was the final slide there, and that is probably the most important part of this operation. Thank you. Thanks for your time.
We've only got 8 minutes left for questions, and you're an inquisitive bunch. We've got 14 questions, but we'll dive into some of the top questions straight away. One of the first ones for Ross here. Can you share your thoughts on the balance between competition and collaboration in the supply chain, and at what point does competition help scale, and when will it become harmful?
Thank you for that question. Yeah, thanks for the question, whoever put that out there.
So our current market in its form was built up thanks to state competition, right? So we had the states were competing each other with various goals. However, we cannot continue to move forward with that type of competition. Competition was able to build up the market, but now we need to take more of a coordinated approach, and states need to seek like the federal. So right now you have the offshore wind state and federal implementation program. State and federal government needs to coordinate more and collaborate on building out the supply chain, looking more regionally instead of looking at local state-based content, looking more at regional or domestic content. And then the other piece I would say on collaboration is, as a part of the study, we also said that there's significant novel issues for the industry here in building out a supply chain. So it's going to also take industry collaboration, project developers, original equipment manufacturers, tier 2, tier 3s, labor unions, academic institutions, and others are going to have to collaborate on building out the supply chain.
Thanks, Ross. I think next one for Pat. I think there's a lot of perhaps hesitant to adopt AUV technology perhaps in the early stages as it grows out, and people opting for probably more traditional based vessel solutions. How do you see the transition between traditional based survey and AUV surveying progressing over time?
Yeah, so that's a great question. I think specifically in the California floating offshore wind, it's going to be very difficult to gather the data of the seafloor with the current surface vessels that we have. It's just really deep, right? And as the wind farms continue to go offshore, it's going to be harder to collect that survey data. So AUVs can be collaborative with surface vessels in that portion of the industry. I think we see in the short term, while we continue to develop the technology and introduce AUVs into the industry, I think you can think of them as like a force multiplier. Surface vessels are limited, and they're extremely important for a lot of different use cases that AUVs just can't do. Like we can't go touch the seafloor, we can't install cables, we can't install infrastructure. So while a high value surface vessel is doing some maybe really strong sub-bottom profiling, you could send a few AUVs out to survey with multi-beam backscatter or side scan and whatnot, and just really decrease the amount of time that surface vessel has to be on station, and thus bend the cost curve down and reduce your survey costs. So I think short answer is collaborative at first, and then as we continue to adopt AUVs in the industry, maybe we start to introduce more of them over time and transition that way.
Thanks, Pat. Melissa, a question for you here. Have you explored what the breakdown transit distance is, and at which a barge solution becomes more optimal than a Jones Act WTIV strategy?
Yes, that was kind of what the pricing did. So Jones Act, we showed up for the long and the short distance that for Salem, the day rate on the Jones Act, if they're both traveling to getting their cargo from Salem, the Jones Act needed to be Jones Act installation vessel. If it was more than 1.13 times the price of the foreign, the day rate was more than 1.13. The foreign would be more expensive. And then same with the going from Brooklyn, it was 1.19 times the price.
Okay. Thanks. Atheendra, a question: Is it feasible to brace the feeder on the platform the way they do for repair support vessels?
Brace the feeder as in like lift the feeder up? Or?
Yep, that's all
Okay.
I've got. Sorry.
Because there is such a design in the works right now. It's one design looks at the feeder going there and the jack-up vessel kind of pushing it down, and another design looks at the jack-up vessel lifting the feeder up completely. It is we need to see where those designs progress and how it works out. But it kind of transfers the critical part from the lifting to the actual lifting of the feeder itself. So that might be driven by kind of the same limits, or the legs of the jackup will have to be designed to be much stronger. There are designs looking at it, but we'll have to see how it works out.
Thanks, Atheendra. Last, maybe one, maybe two. Can we speak to the number of vessels, WIVs, and barges that would be required to meet the 30 gigawatt by 2030 goal? Ross, I don't know if that's something your study is going to be looking at, but certainly maybe there's potential for 10 projects being installed at any one time. Each one's going to need 3 or 4 vessels in terms of the main installation vessels, support vessels. So we're looking at 30, 40 vessels potentially.
Yeah, well, each project, if we're just talking about the number of vessels, and we'll just stick to a regular installation with a wind turbine installation vessel, not in a feedering system, is roughly about 100 or so vessels over the life cycle of the project, both in in your permitting and siting, your construction and installation, your operation and maintenance.
Yeah.
So somewhere around there. And in the report, we have a breakdown of the number of barges, the number of service operation vessels and crew transfer vessels that we project that would be needed for the 30 gigawatts. If we could pull up the slide, we could look at it. But if you're playing at home, you could look at the slide, and that has that information.
Yeah, and the last one, the questions come up a couple of times about the Inflation Reduction Act and the cost benefit trade-off that supply chain, domestic supply chain, and that additional 10% investment tax credits that the Inflation Reduction Act will allow for the use of domestic supply chain. Is that something that the study looks at, or is it staying away from that and waiting for the Treasury to release a little bit more guidance on that front?
So we have, as I said, we have our publication date in January, and part of that got pushed back thanks to having to do a little additional analysis for things such as the Inflation Reduction Act, and as was mentioned earlier, this is, as you mentioned earlier, Jamie. Every day there's a new announcement, a new major manufacturing facility, a new education facility. So we're going to have to cut it. We're cutting it off, but we're going to move forward with information. And we did factor in the Inflation Reduction Act. And I would like to tell you the number of manufacturing facilities that we project that we need for 2030, but you're going to have to wait until January for that. So hopefully now you're all enough intrigued to be reading the report when it comes out in January.
I'm sure if you get Ross a few beers at the networking reception, you might tell you.
Maybe.
Well, I think that's all we've got time for. I'm sorry we didn't get around to everyone's questions. I'm sure the panel would love to take your questions during the break. We're off for 15 minutes, and we're back in the same rooms for the last 2 sessions of the day. So if you take an opportunity to just thank all the presenters today and their time and effort. Thanks, everyone.
Thank you, Jamie.
No, thank you.
started in about a minute and a half. For folks that are still filing in and looking for a seat, please sit in the middle of the rows so that as people join us late, they don't have to walk over or stand. So if you're at the end of a table and there's middle seats available, please scoot over if you don't mind. Thank you. Good afternoon, everyone. We're going to get started now. It's 3:45. We have an hour and a half with you today for this panel session on facilitating ocean area coexistence. Welcome. I want to credit my colleagues at Inspire for this wonderful graphic that shows some, but probably not all, of the activities that will be happening in and around offshore wind farms that have us thinking about how we facilitate ocean area coexistence. Really looking forward to hearing from our panel today, which will speak to some of these activities. I am Emily Shamshinia. I'm the director of the Regional Wildlife Science Collaborative for Offshore Wind, which is a relatively new organization focused on developing a science plan for the U.S. Atlantic coast that identifies the ongoing activities related to research and data collection around wildlife and offshore wind. We are doing this with the assistance of several subject matter experts on marine mammals, sea turtles, birds and bats, habitat and oceanography, some of whom are in the room today and on this panel. So we're really lucky to have the engagement of hundreds of experts on this issue. Just like NOWRDC, we are also maintaining a database of active projects on the Atlantic coast related to wildlife and offshore wind. So if that topic is of interest to you, please visit our website at rwsc.org. I think it got cut off at the bottom of the slide here, or it's very difficult to see. And take a look at our project database. We will soon be moving into the implementation phase of our science plan later next year, where we will begin funding with collaborative funding models from the 4 sectors that developed RWSC: federal agencies, states, offshore wind companies, and ENGOs. Those 4 sectors will begin collaboratively funding offshore wind and wildlife research, and we really look forward to continuing our collaboration with NOWRDC on this and many of you. So recognizing that wildlife is just one of the topics today, we wanted to give you just a quick preview of the speakers you can expect on a range of topics. And because we do have a shortened time period and agenda today, I'm going to go right to our first speaker, Dale Trockle. And I'm going to ask each speaker just to introduce themselves first before presenting the title of your talk and getting into your presentation, and give us a little bit of background maybe on the timing of your research project with NOWRDC, what you have left to go, how much is done, and so on. And lastly, before I do turn it over, I'm told that the Slido has reset, so if you're in the Slido app, you could just refresh it, and there will only be one Q&A session now because there's another session that's a workshop and they're not running a Q&A. So you should just see one option to enter questions. We'll be monitoring that throughout and look forward to your participation in a little bit. All right. I'm going to hand it over to you, Dell.
All right, I'm Dale Trockle with Codar Ocean Sensors. And Codar, for those of you who don't know about it, it's they manufacture high-frequency radar systems to measure the surface currents of the ocean. So here's a picture of one right here. They're shore-based, and they can measure the surface currents over large spatial areas and with a high temporal resolution as well. And I'm going to be talking about how we are working on mitigating the impacts of the offshore wind turbines on that data. And so right here is an example of the kind of ocean surface currents that you get as an output from these radar systems. And each radar individually is able to measure the component of the surface current of the ocean towards it. And so you have to have 2 or more of the radar systems to be able to measure the total velocity of the ocean surface. And our project's goals that we had for this project were twofold. The first part was we were working on trying to be able to better identify the wind turbine interference that gets mixed with our data and be able to flag it better and remove it. And then the second part was to be able to reduce the impact of removing that data. So a lot of the existing techniques work by first estimating the rotation rates of the wind turbines and then using that to identify where in our data we're going to have interference, and then that gets flagged and removed. And when you do that, we're reducing the amount of data we have, and that causes a big loss in the data. And so we're looking at different ways of improving that. And so how the offshore wind turbines impact the HF radars is a little bit different than some of the other radar systems out there because of our high frequency, which when I say that, we're operating between 5 to 43 megahertz. And as the wind turbine spins its blades at each different position, it has a different radar cross-section. And what that means is it reflects back a different amount of energy to the radar depending on what position the blades are in. And since those are rotating, that creates a periodic signal, the amplitude modulated signal that comes back to the radar. And that amplitude modulated signal, when it goes through all our processing, the harmonic components of that show up as wind turbine interference. So down here at the bottom, you can see the wind turbine spinning, and up there is what the amplitude reflected back at the radar is going to look like. And then on the top left, you see the harmonic components. And each one of those will get mapped to a different location in our Doppler spectra. So this plot down here at the bottom is kind of what the radar is seeing. And on the bottom axis, we have Doppler frequency. And on the vertical axis, it's the range from the radar. And these big vertical stripes marked by the yellow arrows, that shows the sea echo, the part that's reflected back from the sea surface, where we get the sea surface current measurements. And then the red arrows going from each of those harmonic components shows where those get mapped in this range Doppler spectra. And this is actually real data from Block Island and from the wind turbines out there right now. And the important thing to take away from this, though, is that each of these get mapped to a specific location, and their location in Doppler frequency depends on the rotation rate. So as the blades spin faster, they go out further towards the edges of the spectra here, and as it slows down, they come back in. And so one of our, as I said earlier, one of the things that previously had been done with the mitigation techniques is to first identify where these peaks are, and then use that to estimate the rotation rate and go back and subtract that away. So if it ends up that one of these peaks gets moved into the sea echo, then we have to remove it so we don't process that and think that it's sea surface current or sea echo when it's not. And so when that data gets flagged, it's just removed and not in there anymore. And so one of the ways which we tried to mitigate that is by using multiple different radars to measure the same patch of the ocean. So in this case, we have 3 different radar sites at Cedar Island, Little Island, and Duck. And then we have an example of where the offshore wind turbines are there. And then also out there with some vectors that are representing the sea surface current at that area. The blue one represents the actual velocity of the sea surface out at that location. And then all the colored arrows represent the component, the radial component that each of the radar sites are measuring. So you can see that that radial component, the component towards each of the radars, is going to be different at each of the 3 different sites, which is a really good thing, because that means that when we go in and flag that, also before I said the rotation rate dictates exactly where the wind turbine interference is going to get mapped. So since the rotation rate of the turbines is going to be the same at all 3 sites, then if we flag that data and remove it, it's going to only be removed from at most one of the radar sites. In addition to just using 3 different sites, we also operated 2 of those sites bistatically, which means that we transmit from one radar and then receive it at another one. And so when we operate our radars this way, typically we have them that each radar, when they're operating monostatically, transmits and receives at the same site. But we can also transmit, receive from that site, and then adjust the timing at a secondary site so that we receive that signal as well. So this portion of the spectra right in the middle here of this plot, that's the signal from the first site that was transmitted from that site and received from the site. And then the top signal that you see up at the top of that spectra, that is an example of the signal received from when it was transmitted from a second site and received at the first site. And by using these strategies of both using it bistatically and using multiple turbines, we wanted to see, or multiple radars, we wanted to see if we were able to reduce the impact to the oceanographic measurements that we were getting from the radars. And so what we did is we went in and we deleted, or we flagged data in the sea echo representative of how it would get flagged for the wind turbine interference mitigation that we were using at all 3 sites. And then we reprocessed the data to see how much data was lost by doing this. And when we just used 2 sites, Duck and Cedar, we ended up losing 1,621 ocean surface observations. And by including just one more site, we were able to reduce the amount of data loss by an order of magnitude. And then adding, our third test was to use the 3 sites, but then operate Little Island and Duck in bistatic mode so that Little Island received the signal from Duck as well. And that again reduced the amount of data lost a little bit further, but obviously as you add more and more radars, the amount of reduction you're going to get is going to be diminishing returns each time you add new information. So this is pretty easy to understand why this works. Basically, we're saying if you have redundant information, the more redundant information you have, the easier it is to recover that if you delete some of it. It's not so sensitive to removing the data. And then for our second goal of the project was to see if we could actually identify the wind turbine interference better, because if we can identify it, then we can flag it better and have better success that way. Previously, what we did when we were funded under an effort funded by BOEM is we would go and find the interference peaks from the wind turbines and then look at their location and invert the problem to say, okay, we know what the rotation rate is now, but what, and then we could go back and flag anything. And this was useful particularly if the interference got mixed with the sea echo where you can't see it. We could use this stuff away from the sea echo to be able to estimate the rotation rate to then identify interference that was mixed with the sea echo. And so what we tried to do under our effort right now, what we've done is to, rather than doing that by hand and trying to find those specifically, we'd wanted to try to use machine learning techniques to be able to identify the rotation rates and then do that hopefully with a more accurate method. And when we applied that, we were able to use our machine learning algorithm to estimate the rotation rate of the turbines from the CSON cross spectra, or from the radar cross spectra that I showed you. Just using that as an input, we were able to estimate it with a root mean squared error of about 0.096 rotations per minute and a standard deviation of 0.25. And that number is really important because that means it's below the amount in a single Doppler cell, so we're able to perfectly identify it for this scenario. And then we also, the other plots that you see up here, we also wanted to see how well we could predict the rotation rate variation, and because that impacts how the interference peaks get spread out if it's varying a lot over a Doppler collection period. So usually that's about 16 minutes of data we collect to be able to do a Doppler transform, Fourier transform. And we also wanted to see how well we could predict yaw angles, because the yaw angles impact how the amplitude of the different interference peaks. And so just to show why variation the variation of the rotation rate over that 16-minute period is important. On the plot on the left, we have we have two different examples of what those interference peak would look like depending on how it varied. If it varies linearly, like slowly increasing from the start to finish of the 16-minute period versus oscillating up and down, greatly changes that. And so because of that, we concluded that we were not going to be able to estimate rotation rates at a high enough temporal resolution to be able to resolve that perfectly. And we have moved on and decided just to stick with the flagging for now. And for my final remarks, or just key takeaway and results, are basically the impacts of flagging and removing data that we were using previously. If we were doing that by using more radars and operating them bistatically, we're able to have redundant information and be able to mitigate that impact quite a lot. And then rotation rates can be estimated a lot better with our machine learning techniques. We've shown that we're able to get pretty good estimations with that, and that unfortunately the short-term rotation rate variation is too complicated to be able to accurately represent in just subtracted way and keep the sea surface current measurement from that location. And our next steps are we're going to be testing on the field sites and trying to quantify the improvements when we use both of these ideas together, both the machine learning to improve the rotation rate estimation and the multiple radars to be able to backfill any data that gets removed. And we're also still looking for more higher resolution rotation rate data sets that we can get from the actual turbines when we have the radars operating, so that we can validate some of our methods a little bit more and test it. That's all I've got.
All right, just a reminder that if you have questions, to put them in Slido, and we'll visit those at the end. I'm going to introduce now Aaron Rice from Cornell, who's going to talk about right wind, resolving protected species space use conflicts in wind energy areas.
Thanks. So I'm Aaron Rice. I'm at Cornell's Center for Conservation Bioacoustics, and in this particular project, we are working with the New England Aquarium and a locally based consulting firm, LawTech, that lets us get at sort of a bunch of different perspectives on protected species issues with respect to offshore wind development. So just want to acknowledge my co-authors. So I'm sure all of you have seen this particular map ad nauseum over the course of the day. But with all of the wind planning projects along the Atlantic, there's been a number of baseline biological surveys for marine protected species that have been occurring. And so many of these, we started doing work in some of the early stage offshore wind development, around 2010. Projects have been coming online more recently. And fundamentally, the question starts to become, well, what do you do with baseline data on marine protected species? How can you use this from the perspective of improving the success of construction and operations? And when you look at this map with the lease areas and the project areas, what immediately comes to mind for those of us on the environmental side are the space use conflicts with North Atlantic right whales. So the right whales are a endangered marine mammal that use this particular corridor as part of their key migratory habitat. And in many of these wind lease areas, they overlap specifically with seasonal management zones for right whales. And so while the government agencies and industry have both been funding an extensive number of baseline surveys, it's really unclear, again, what do you do with this? And then some of the projects have had acoustic surveys, others have had aerial surveys. There's been a couple where both have been done, but again, then the question becomes, well, how do you integrate multimodal survey data? And so with all of this, fundamentally, offshore wind development requires mitigating impacts to marine protected species. These are both federal and state statutes. And the challenge we get into is that simple occurrence models or presence-absence predictions of things like right whales are often insufficient to inform planning. And what has happened in recent years is that right whale movements have become different or are shifting from baseline patterns. And so we have now an increased variability in cetacean movement through these areas that increases the difficulty in planning. And this uncertainty starts to create risk to developers. And so what our goal is to take an extensive amount of baseline data and use this in a way to both deconflict and de-risk wind energy development. And so many of you also may have seen this. These are the spatial density models from Duke that take visual survey data of cetaceans over the past 20 or 30 years and then be able to look at it from the probability of occurrence. The challenge is, and the Duke folks will say this themselves, that these maps are designed to be interpreted really at a continental scale and not specifically for individual projects. And so the grand, a zoomed in version such as around Massachusetts, may show a predicted density of animals at a certain point in time, but this is asking more of the models than they're really capable of providing. And so what we need to do is generate more specific species distribution models that are specifically aligned with the conditions at offshore wind sites. And so here, what we wanted to do is not only take the protected species data, but then use that to create what we're calling a decision support tool, using both biological data on species occurrence as well as environmental data for prediction and forecasting, combine that with a financial perspective on construction costs to be able to allow different agencies and industry to do some degree of prediction. And being able to look at when there's going to be construction timelines, or it's when construction is scheduled for certain times of the year, what is the risk to that construction schedule? And for this particular project, we've been focusing on the Massachusetts, Rhode Island wind energy area, but and that's largely due to the extensive amount of data that have been collected. But our approach, we're hoping, is scalable to any particular wind area location along the Atlantic coast. So we've just cleared the phase 1 of the project and moving quickly into phases 2 and hopefully phase 3. But our overall project has 3 specific objectives. One is to use aerial and acoustic survey data to develop predictive models of whale occurrence. We want to understand what's the level of uncertainty that these models begin to generate in terms of when and where are whales going to be occurring, and then use those data and pivot to the financial risk assessment scenarios. And this is specifically where we can leverage the talent and expertise of our partner LawTech. So when you see this, here we have the map. In the background is the Massachusetts, Rhode Island wind energy areas. Overlaid on top of this in somewhat of a mess of a map you see these vertical white lines. Those are aerial transect lines flown by the New England Aquarium. And you may see white dots in the background. Those are the locations of individual sightings. And then those circles are the locations of some of our bottom-mounted passive acoustic instruments, showing two different detection ranges. That smaller purple circle is the detection range for North Atlantic right whales under elevated noise conditions, and then that pink circle is the detection range for North Atlantic right whales under median and lower noise conditions. And so what we wanted to do is take these overlapping data sets and ask the question that when we have concurrence in the alignment of both surveys, what's the probability of detection and what are the occurrence patterns that we start to see in the occurrence of North Atlantic right whales during similar periods. And to give you an idea of sort of data alignment, this starts to show a timeline with month, sensor on the x-axis, and then timeline or by year on the y-axis. Those blue vertical bars that you're seeing are the number of flights, usually 2 per month, that the New England Aquarium had conducted, starting in about 2011, going until 2021. And then those horizontal pink bars demonstrate the sort of when we had acoustic recorders in the water. And you can see that between 2011 and 2015, there's an extensive amount of coverage from both. And then the New England Aquarium continued to fly aerial surveys. And so if you look at these two different maps, these are the types of data and the types of stories that we start to see from each different survey method. So on the left-hand side, with that 9 boxes, are basically right whale sightings per year, going from 2012 to 2021. And what we begin to see is a shift in the spatial distribution of North Atlantic right whales. Early on, we're starting to see animals primarily occurring in the north, a little bit in the east. We see an increase over time in the sightings of right whales in this area, and then in recent years, a concentration of right whales on the eastern side of that wind energy area. And on the acoustic survey side, what those circles represent are the detection range of different sensors with a 22-kilometer buffer, and the color ramp, those warmer colors represent a higher concentration of things like upcalls or acoustic detections from the right whales, and you can see that in our last year, significantly higher levels of detections from previous years. And so what we can do is start to generate a timeline of occurrence. So over many years, these are the seasonal perspectives that we start to get on right whale occurrence. So with aerial surveys on the left, you can see that aerial surveys are primarily identifying animals in the spring, a drop-off in the summer, a slight increase in the fall. And then with the acoustic surveys, again, it's echoing that pattern, except what I want to point out is that in months like May, June, July, August, when the aerial surveys and acoustic surveys had decreased number of observations, it's still not zero. And so these data begin to demonstrate that right whales are in and around the Massachusetts wind energy area for the vast majority of the year, albeit in differing levels. So what we did was take these data into a predictive spatial species distribution model. Here we're using occupancy modeling, but there's a number of other modeling methods that we're going to use. And the warmer colors on that sort of overlay map that you see on top of the wind energy area, the greens and yellows are a higher probability of occupancy. And so in the spring, which you see in that box in the upper left, or excuse me, the upper right, there's a higher probability of occupancy of whales across the entire area. And then in winter, summer, and fall, significantly lower occupancy of right whales. That being said, for all seasons, you still see a increased probability of right whales in and along Nantucket shoals. And then the other question too is, with these model predictions, what's our level of uncertainty? Certainly we can't we're limited in inference and understanding of what the implications of data are if we're not understanding the uncertainty. And so with this broader perspective of occupancy, there's two different components with different ecological processes. One is this idea of colonization, which is animals coming into the habitat, which are those 4 panels that you see on the left, and then this idea of persistence, with those 4 panels you see on the right, which are animals remaining in the area. And what we see is greater uncertainty in places where the models are estimating higher occupancy, and then lower uncertainty in places where there's lower occupancy. And so we see, again, lower uncertainty in the areas towards the north. What we also see is there's not a direct correspondence between the aerial and the acoustic survey data, and initially we were kind of distressed about this, but what our takeaway is that the fact that we're starting to see slightly different messages emerge from the 2 different data sets begins to suggest that the 2 methods are complementary rather than redundant, and we can use the 2 of them together to start to have a more holistic understanding of right whale occurrence in and around wind energy areas. And we do see an overall correlation with the number of calls detected with the number of animals that are observed. So, what we have here is the combination of survey data shows year-round occurrence of right whales in and around the Massachusetts wind energy areas. We see low uncertainty in most places, and these ideas of being able to have multiple survey methods may yield more insight for understanding protected species occurrence in fundamentally animals that are difficult to observe and seem to not want to be found. So our goal is using the Massachusetts wind energy area as a pilot, but being able to apply to other species and other wind energy areas. And so, what we're doing is taking the distribution data from phase 1 and then pivoting to these financial forecasting models in phase 2, as well as being able to incorporate oceanographic data into the occurrence models for improved protected species forecasting. And so our project partner, LawTech, has this product called ESOX, which is weather downtime modeling, where they can look at weather forecasts for the coming construction seasons and identify how many days of construction would be lost due to adverse weather. And so one of the products that we could envision resulting from this project is a combination of not only a weather-related downtime, but protected species related downtime for forecasting construction timeline. So leave it there. Thanks.
All right. Continuing on the marine mammal theme, we're going to go to Carl Kaiser now from Saildrone, who's going to talk about uncrewed mobile assets to monitor protected marine mammals. Welcome, Carl.
All right, great, thank you. I want to thank the session chair for organizing this and Aaron for basically making the case for why all this is needed. That makes my job a lot easier, so thank you both. What we're going to talk about is an uncrewed way to potentially monitor for and therefore mitigate these marine mammals. First of all, why do we need this? Okay, same slide. It's also legally mandated. So it's not just what you need to do, it's actually what you absolutely have to do. There's no choice about this. It costs a lot of money, and so anything that makes that cheaper brings down that levelized cost of energy. So it's a very important thing to do, as well as being the responsible thing to do. So why uncrewed? Well, there's a lot of reasons. Presently, this can be anywhere from 1 to 3 crewed vessels. Crewed vessels have a big environmental footprint, which is what we're trying to mitigate, right? They have to have space for people to live on. They cost money because you have to pay all those people. Uncrewed vehicles, they can be very small, they can be very high capability, they can be largely renewably powered, which is what we're going to talk about specifically here. And they can have a lot of persistence, they keep people out of harm's way. So Saildrone itself, for those who aren't familiar, is actually gotten to be a fairly big operation. The concept was about 2010, but the company was really formed in 2016. But it's taken off a little bit, as you can see. This is the mothership office out in Alameda, California. You can see the sort of production line aspect of building these drones. They're used in a lot of different things. My marketing people would love me to tell you all about them, and I will if we have time. We won't have time. Okay. So, but you can see it's a pretty big operation. Offices now open in Fall River, Massachusetts. That's where I'm based, as well as Washington, D.C. and St. Petersburg, Florida. Also talking probably soon to be a couple of other offices around the country. So we're spreading out. We're going where our customers are and focusing on things that they need us to focus on. I will just mention The whole thing is American owned. The supply chain is mostly in the US, and it's largely able to meet both the domestic production goals that I keep hearing tossed around here, but in other industries that's very important as well. So we're now north of 22,000 days at sea, closing in on 1 million miles sailed, and all over the world. I didn't put in the map, but we've been up to the high Arctic, we've been down to the Southern Ocean. Because of COVID restrictions, we had this great mission recently where we couldn't get to South Africa to launch, but needed to be off of South Africa, so we launched in Rhode Island, sailed to South Africa, did our mission, and sailed back to Rhode Island. So it's got a good track record. We're partnered on this initiative with RPS, so they're sort of one of the world's leaders in offshore passive acoustic monitoring. They helped write and are helping write a lot of these mitigation plans, and they've got some really great ML algorithms, so it'd be remiss if I didn't mention that. We're looking forward to working with them. And then our most fame recently, this is out of the eye wall of Fiona. So we've been through Category 4 hurricanes on a couple of occasions. We got in behind Ian, but we could never actually get into the eye itself. So you don't really have to worry about these things in the northeastern conditions. On the other hand, you won't get acoustics in that, I promise. So now let's get into the actual details. What do we have? We have 3 vessels. The Explorer, that's that workhorse class that you saw on the production line. It's a 23-foot vessel. That's what we'll be starting this project with. And then that is entirely renewably powered. So that is solar power and wind power. So essentially 0 carbon footprint. The Voyager's a little bigger, 33-foot class vessel. We've got, I think, 7 of those now, something like that. That changes on a daily basis because we're just ramping up production. So those are getting pretty well wrangled. We will be finishing this project on the Voyager class vehicles, which is probably the workhorse for this offshore wind energy. It's the same basic concept. It's mostly wind powered. It's mostly solar powered. But the nice thing is we have a diesel generator on there that we can crank up, and that gives us a lot more power capacity to play with. It lets us really expand our sensor capabilities so that you can go multimodal, so that you can go both, for example, visual, thermal, and acoustic on the same boat. And then, not really relevant to this, we also have the 72-foot class vessel, which is mainly a bathymetry platform and a few other maritime domain awareness types of things. So let's focus in on this Explorer. It's only 1,500 pounds. You can pack several of them in a shipping container and move them around real easily. But as I already mentioned, we're setting up a Northeastern Operations Center here. Longest mission was over 370 days without service. Little asterisk on that, they did actually sail it by the Canary Islands where some guy went out in a boat and scrubbed the hull down a little bit with a brush. But that was just once. And these are really what we've got out there. About 3 knots. So they're not fast, but they're fast enough. They get there. I mentioned this one. This is more of a 5-knot vehicle. It's also got an auxiliary prop, so even 8-knot sprint speed, which could be important for maneuvering. But it's really that 1,200 watts of power. That means things like LiDARs can go on there. Makes this a really flexible platform. All right, so what are we actually doing? Why are we all here today? This is what we're planning on doing. We're putting a passive acoustic keel array on these things. This is an Explorer out here in San Francisco Harbor. It's got a keel array on it. That is the only picture you're going to see today of the keel array, and that is by dictate of the lawyers. Sorry. We will, I promise, next time we're here, show all of that, but there's a couple patents that have to be filed first. So we've been developing that keel array on IRAD. As of right now, we're not under contract yet, but that's actually sort of to plan. We had agreed that we would do a certain level under IRAD, and we're still in that schedule time frame. But that brings up, Julian wanted me to mention, if you are interested in being on the advisory board for this, please email him, because that's not formed yet. So we'll have this passive acoustic keel array that will come up to the Saildrone Explorer. We're already satellite comms enabled. Right now it's Certus, which is relatively low bandwidth, but we've got several new things in the prototype stage where we'll be fairly high bandwidth real-time linked in the near future, either all the way back to shore or to a mother vessel. So the plan is we will send whatever level of data we need to. In the short term, that'll be a lot. Hopefully in the long term, that'll be very little as Edge AI comes into this. We'll go to the AWS, Amazon Web Services backend. That lets us do anything we need to at any compute scale that we need to. We'll also go directly into the PAMGuard API. That's sort of the industry best practice for looking at these acoustic data in real time right now. And so our goal in the short term is not to take the acoustic observer out of the game. Our goal is to take the acoustic observer off the ocean and put them on their couch, which is a safer, cheaper place to have them. So, and then in the even in the course of this, but certainly in the longer term, RPS has been developing machine learning algorithms to pick out these whale calls, a number of other groups as well, Cornell, lots of other people. So we do have Edge AI capability on these. We have Jetson AGXs on there, and on the Voyager class actually have more compute power than, I won't say than you can use, but than you should use. So anybody can use as much as they can have. But so we'll eventually be pushing out to Edge AI, but that technology is not ready yet from anybody. And even if somebody says, yes, mine is that good, it's still not regulatory approved yet. So we'll start crawl, walk, run, right? And then you can also get everything on our mission portal front end, which gives you the synoptic view from anything else. You can log onto that from any web browser in the world. As long as you've been tagged access to that drone, you can see it. You can ask it to go somewhere else. You can do all kinds of things. All right, so I mentioned the IRAD preliminary results. I was hired about 9 months ago along with the three other people in the acoustics group, so we're pretty preliminary. We did a market survey, ended up building our own system. 7 channels as of about a month ago. You can see this is a liquid natural gas tanker out in San Francisco Bay, about 3 miles away. That's the acoustic equivalent of, can you see a barn standing right in front of you? But yes, we can. We can also break the left-right ambiguity. We've got nice clean, you'll notice there's not a lot of fuzz out here. So it's a nice clean signal. It should be a good platform to work from. Beyond that, we actually did take it out off of Provincetown and got these actual, I'm told, humpback whale. I can see whale, but I can't see species. But I'm told by the experts that's a humpback whale. So we were able to pick those off, but we haven't got ground truth yet. So that's really where we want to go with this project, right? We're planning 4 field ops. This is all about a data collect and improvement and validation process here, right? So first field op is just to get this thing out. Our IRAD funding, as allocated by our board, is much more heavily focused on maritime domain awareness, but now with this, we can really move more rapidly into the marine mammal space than we thought we could. So get out. We want to overlap the Cornell buoys, probably up in Cape Cod Bay. So I was really excited to meet Aaron, get ground truth. And then the next mission out will sort of be, okay, how do we actually have to drive these things? Like, there's a couple of vehicles. How are we going to coordinate those? How are we going to make sure we have good coverage? Like, there's a real ConOps problem here that we still have to solve. We can draw a lot from the crewed vessel world. Third mission, now we're doing it over the satellite link, pushing all the way to RPS observers, certified observers who are going to be hopefully sitting on their couch. If they want to sit at a desk, I don't really mind, whatever. Fourth mission, this is all up for a month. We will be out there on station in a simulated, in hopefully an actual lease block, which may or may not be under active construction, but we'll try hard to time it so that there are construction vessels or other acoustic monitoring vessels out there, really get ground truth, really get market validation. So that's basically where we're going. I would get scalped by my marketing department if I didn't put this slide up there and just mention that Saildrone has capabilities in lots of aspects of the offshore wind life cycle, not just the marine mammal stuff, but you guys really came here, I think, for the mammal stuff. So with that, I think I yield my last 8 seconds back to the chair.
Thanks very much, Carl. And you guys were just awarded funding in the most recent round, right? So you're giving us kind of a sneak peek on the project as it's developing.
That's correct. Yeah, we were awarded in August or September, and I hopefully will be under contract soon.
Awesome, thank you. All right, I think we got a few backup slides to click through here. Shifting gears now pretty drastically. The next talk is from Rebecca Green from NREL, and she's going to talk about co-design solutions for floating offshore wind and fishing compatibility. And I would be remiss not to mention, so I mentioned that I'm from the Regional Wildlife Science Collaborative for Offshore Wind. We have a sister organization called the Responsible Offshore Science Alliance that deals with fisheries in that industry and the monitoring and different, data collection activities that are going on the Atlantic coast. We work very closely together. Rebecca's going to talk about that, but I just wanted to be clear, the group that I represent doesn't have anything to do with fish and fisheries, but ROSA does, and so we're really lucky to have them as a partner, and thanks for talking about this today, Rebecca.
Excellent. My pleasure, and thank you, Emily. As Emily said, my name is Rebecca Green. I've been with NREL now for a little over 4 years. I work on a variety of environmental, siting, human use, and fishing aspects, all related to offshore wind. I've worked in the offshore and marine sciences for a little over 25 years, and it's really exciting to be back in Boston. I got my PhD from the MIT Woods Hole Oceanographic Institution Joint Program, which was really just a great part of my life. So like I said, it's great to be back here. So I'm also going to be talking with you about a project that was awarded by NOWRDC under the most recent solicitation. So it hasn't actually been contracted yet. We're in contracting, so I won't have any data to show you, but I can give you a preview of what we're planning to do as part of this project. The title of the project, as you can see, is Co-Design Solutions for U.S. Floating Offshore Wind and Fishing Compatibility. So by way of a little background, you heard during our plenary talks this morning about how important we believe floating offshore wind is and will be in terms of achieving administration targets for offshore wind. Given this widespread development of offshore wind using floating technologies, it's anticipated in the U.S. that there will be potential displacement of important recreational and commercial fisheries. Floating offshore wind, just as a reminder, applies across all U.S. regions, the Great Lakes, Atlantic coast, Gulf of Mexico, and Pacific. So this is relevant around U.S. coastal waters. There are unique challenges to minimizing interactions between the floating offshore wind balance of system that have not entirely been part of the fixed bottom wind conversation with fishermen thus far in the United States. So we see a real opportunity here to fill in those gaps. There are several components associated with floating turbines that are relevant to this project and that balance of system, including the substructure or platform, the mooring lines, the dynamic power cables, and associated anchors. And these all have the potential to interact with commercial and recreational fishing gear and to potentially limit fishing access. This is just an example of a couple of different floating offshore wind designs with different mooring line configurations and different platforms, as you can see here. Fortunately, U.S. floating wind designs are still being developed, so there's a real opportunity here to co-design early in the process of development and construction novel floating wind technology solutions that we believe can help to reduce potential siting conflicts, mitigate risk of interactions with the fishing industry, and lower overall project costs for floating offshore wind in the United States. In terms of our project team, NREL is, we're leading the project. We're also bringing to bear our suite of floating wind mooring design tools. So really excited to work together with Matt Hall and our team from NREL on that aspect. In terms of related projects and what we've done in the past in this regard, we're just finishing for NYSERDA a fishing access project associated with fixed bottoms foundations in the New York Bight. And just published that, and I'll show that on the last slide so that you can access it if you're interested. We also have related NOWRDC projects associated with shared and standardized floating mooring designs, and are currently working on a FOA 2236 project with the University of Maine associated with a synthetic mooring alternative design. Our partners on this project are ROSA, the Responsible Offshore Science Alliance, who bring fishing industry engagement in the Central Atlantic and have a wealth of related expertise in this regard in terms of regional research and monitoring associated with fisheries and offshore wind. Another partner is the University of Maine, who will bring to the project fishing industry engagement in the Gulf of Maine. And I've also listed some of their related projects here on the slide. Fishing industry is part of the project from the start. I haven't listed names here again because we're still in the contracting phase. But from day one of the project, we will have the involvement of commercial and recreational fishermen as part of our participatory co-design process. And then we'll also have a project advisory committee, as all NOWRDC projects have, including with participation from developers, a mooring company, state agencies, and federal regulatory agencies. So our overall objective is to develop novel floating array design concepts for the U.S. industry through a co-design process with U.S. commercial and recreational fishermen that optimizes the potential for floating wind farms to coexist with fishing activities. This is an overall synopsis of our project here. Once we get started, we anticipate a period of performance of about 30 months with participation from the states of Maine, New Jersey, as well as industry support. I've talked a little bit about our experience. In terms of our approach, we'll be implementing 2 different case studies, one with lobstermen in the Gulf of Maine, and the second in the Central Atlantic with select commercial and recreational mobile gear fisheries. Also talk a little bit about the innovations we hope to bring on this slide, impacts in terms of maximizing coexistence. We'll be looking at the economic impacts by performing a cost-benefit analysis on the solutions that we develop for the 2 different case studies, and ultimately bringing to bear, hopefully, fishing-friendly floating wind designs. We have 4 different goals. The first is to develop and apply a fishing co-design framework. So that will be the very first task that we'll develop in this project. The second will be, or alongside this first task, will be to prioritize focal fisheries requirements based on the outcomes of conducting semi-structured interviews with the commercial and recreational fishery participants. We have some background in this work based on the NYSERDA work that we've just finished up working together with partners. And this isn't just an example of some of the numerous different variables that we're going to look at optimizing as part of this project. Not only turbine spacing, but turbine size, different profiles for the mooring system, power cables, and anchoring. So this is just an initial schematic that we had in our proposal showing what sorts of variables we're looking to optimize, but we may include others as well. As I said, we'll be conducting 2 different case studies in the Gulf of Maine and the Central Atlantic. We've seen where the Central Atlantic now is exploring some areas through BOEM's recent announcement for floating offshore wind, so very relevant timing in that regard. And then ultimately, providing recommendations for technology solutions that optimize the potential for coexistence between floating and fishing activities. We'll be performing the cost-benefit analysis that I mentioned to quantify fishing access metrics and costs, logistics, and LCOE analysis of the case study designs. By way of deliverables, we'll be providing the results of the interviews conducted in the 2 different regions, our fishing co-design framework, the case study outcomes, the benefits analysis that I referred to, as well as final reporting, a publication, and advisory board involvement throughout the project. And finally, I just wanted to mention, again, since I don't have any data to show you from this project yet, a related recent publication that we just finished up. This was a NYSERDA-funded project that we are getting ready to complete on New York Bight offshore wind farms and going through a collaborative development process of strategies and tools to address commercial fishing access, specifically with the scallop and surf clam ocean quahog industries in the New York Bight, associated with fixed bottom foundations. So this new project will be a really nice next step, going from fixed bottom to floating designs. We worked together, NREL did, with Rhoda and the Global Marine Group on that project. So I'll just say that if anybody's interested, this report is now out there, including at the below link, and I'd be happy to talk with anyone about that project. Feel free to contact me at any time at this email address, and thank you for listening.
Thanks very much, Rebecca. All right, our final talk today is from Andy Myers about ensuring long-term availability and bankability of offshore wind through hurricane risk assessment and mitigation. I thought it was kind of funny that this made it into this session because the coexistence options for some of the other topics, we have a choice, but with this one, we really don't have a choice. It's hurricane or no hurricane. So really looking forward to hearing about this, Andy. Thanks.
Great. Yes, thank you, Emily. Yes, so I'm Andy Myers. I'm a professor of structural engineering here at Northeastern University. My background is in earthquake engineering, as are the backgrounds of many of my team members, where lots and lots of research has gone into assessing risk of natural catastrophes, earthquakes, to infrastructure. So we are bringing that background to assess hurricane risk to offshore wind energy infrastructure. Our team has been working together for about a decade, so we have some prior work to build on, but we also are well aware of the limitations of what we've done previously, and we were thrilled to get this NOWRDC project to overcome those limitations. So most of what I'm doing today is kind of laying out the background of our project, the scope of our project, and then some initial results. We're about 3/8 of the way through our project right now. Yes, all that. Okay, so the objectives of our project. Like I mentioned, I've been, as soon as I came to Northeastern 11 years ago, I kind of realized that my background in risk and my passion for climate issues intersect with respect to offshore wind and hurricanes. So we wrote proposals on that right off the bat. And so we had a project that started almost a decade ago that was looking at assessing hurricane risk to mid-Atlantic and North Atlantic offshore wind energy infrastructure. I can tell you, having given presentations on this topic for a long time, that a front-of-mind question on many folks that I speak to is what's going to happen to these farms when a hurricane hits. It's a sort of scary idea, but we have very rational tools that we can use to assess the risk numerically from a downtime perspective, from a cost of damage perspective, in order to demystify hurricane risk. Our hypothesis is that the perceived risk is quite a bit higher than the actual risk, and so we're going to build some industry confidence by making new tools and methods to assess the risk rationally. We're going to assess that risk for U.S. scenarios as part of this project, and very importantly, an area where our current project did not have enough time to fulfill is we're going to translate this to industry in order to generate industry best practices. Very grateful for our sponsors. So NOWRDC is a sponsor, as well as 3 individual states. We're sponsored by the state of Massachusetts, the state of Maryland, and the state of New Jersey. So we've got a broad interdisciplinary team from Northeastern. Jerry Hajar, an expert in steel structures, and myself are on the team. We are the PIs of the team. From UMass Amherst, we have Sanjay Arwada. He's an expert in structural reliability. At Johns Hopkins University, we have Ben Schaefer, an expert in design standards for structures. Benjamin Hobbs, an environmental engineer who does work on assessing resource adequacy of grids, as well as the economics of grid reliability. Out in Colorado Boulder, we have Professor Julie Lundquist. She's an atmospheric scientist who does high-resolution large eddy simulations of wind fields. In Clemson University, we have Wei Cheng Pang, an expert in assessing hurricane hazard risk, how often hurricanes occur, how intense they'll be, and what are their characteristics. And then here at Tufts University, we have Eric Hines, another earthquake engineer and structural designer. So the motivating problem here, we have a 40-year-old industry in Europe, mature, learned a lot. They've got 30 gigawatts of experience, but they don't have hurricanes. Asia is exploding in terms of their installations. The last I checked, there are about 20 gigawatts of capacity, but everything's really recent. And they do have hurricanes there, or typhoons, but everything's recent, so we don't have a lot of historical background to build on. So this lack of global experience seeds doubt within the industry. As I mentioned before, the perceived risk is quite high. One particular industry, an industry I used to work in, that is highly influenced by this risk is the insurance and certification industry. And they are very concerned about potential bottlenecks in overall global insurance capacity for offshore wind farms if the risk is not kind of more confidently and there's consensus on what it is. This is a problem identified clearly as a key research need by the Department of Energy. And very clearly, the offshore wind energy industry is a regional industry. Hurricanes are a regional risk. It's a regional problem needing a regional solution. Okay, so prior work. We did a study where we looked at, from 2018, the wind energy areas, and we assessed the annual probability of failure, structural failure due to hurricanes for the locations of the wind energy areas of that time. You can break up risk assessments into 4 basic components. The first is assessing the hazard. So in the case of hurricanes, that's assessing the wind conditions and the wave conditions. Next is assessing the structural loading caused by those hazards. So what are the stresses and overturning moments caused by the wind and wave. The third is assessing the fragility. So given some structural loading, what is the chance of damage? And putting all those 3 pieces together, you can then calculate risk. You can calculate probability of failure and associate that with dollars, insurance losses, downtime, and things like that. So this project was great. It's the foundation of our NOWRDC project. But it identified some key issues. Number 1 is we did crude parametric modeling of the wind fields and of the wave fields. Number 2, at that time, the kind of only widely used turbine that was out there was the 5 megawatt NREL turbine. So we got to up that now to the 15 megawatt IEA turbine. A third issue is that we did not assess impact to grids. So obviously it's people that are using this electricity and the grid reliability tied to the offshore wind farms. Tying that together is a key part of understanding the impact. And then a final objective is we need to then translate this to codes, to certification bodies, and to insurers in order to make sure that this learning has impact. All right, some other prior work that we did. So this is supposed to be an animation, but I think I'm in PDF, so it's not. It's a gorgeous animation of a large eddy simulation of a hurricane wind field. You can clearly see the eye wall. These little red, when it's animated, you can kind of see them moving around in circles. These little red bits are areas atmospheric scientists call them mesovortices. I call them tornadoes inside of hurricane eye walls. They are very detailed structures of the hurricane wind field that have an impact on structural loading. 2 areas in particular where they have an impact is wind field veer. So this is wind direction changing with elevation. Wind farms rely on the ability to park and feather the blades in the event of a hurricane, but if the wind field is changing direction as you move up, there is no parked and feathered condition because that relies on sort of a single wind direction. Another issue too is very quick direction changes. These mesovortices cause direction changes that potentially might be faster than the system can respond to and to orient itself into the parked and feathered condition. So this was some previous work that we did. This is for a Cat 5 hurricane, which is kind of so unlikely for the mid and North Atlantic that it sort of isn't relevant. And so this project will let us do large eddy simulations for more relevant storms for the US Atlantic coast. The work we did previously is, so we looked at these large eddy simulations, we looked at detailed wind fields, and then we saw how they affected structural loading compared to just kind of normal rated conditions. And then compared to the facts of these higher gust factors, of the fact the wind is veering in the case of a hurricane, and the fact that there are very fast direction changes. All right, so the first task of our project is to develop this, what's called a stochastic hurricane catalog. So hurricane risk, since there's such a short historical record of hurricane activity, and there are so many possibilities of hurricane scenarios that we haven't observed in the historical record, the way that we assess risk is we create synthetic hurricanes that are statistically compatible with the historical record. So out of Clemson University, we've got a catalog that represents 100,000 years of potential hurricane scenarios to kind of more completely understand what's possible for hurricane tracks and hurricanes intensities. As part of this, we're going to determine typical characteristics that will be used for the large eddy simulation. Just got my clock here. We're doing large eddy simulations. So like I mentioned, our previous work was at Cat 5. That's too extreme to be relevant for the Atlantic coast. So now we're doing Cat 1, Cat 2, and Cat 3 to get a better feel of detailed wind fields at more realistic intensities. We're going to be using physics-based wind field modeling and wave field modeling in order to create hazard maps that are useful for understanding what the risk, the exposure of particular sites are to hurricanes. So these are kind of wind-wave combinations that you can then tie to mean return periods that are useful for designers and to decision makers. Fourth task is that we are going to address the impact of hurricane scenarios on offshore wind development on the resource adequacy, focusing mainly on the PJM energy market, but also looking at the New England ISO market. So this is trying to understand what happens if an event happened that causes loss in capacity of an offshore wind farm. What's the impact to people? How long is the capacity going to be down? And how impactful is that loss of capacity going to be to the users of the energy within the regions that are affected by it? Task number 5 is we put this all together in order to analyze scenarios and actually calculate dollars in downtime associated with hurricane risk. And task number 6 is translating this into industry. So we've spent a lot of effort in developing a comprehensive industry advisory board. We had our advisory board kickoff meeting in June. We had 37 attendees. We have developers, we have financiers and insurers on this committee. We have grid managers, we have certification bodies, and lots of developers and consultants and lots of folks who are stakeholders and want to know the impact. I am running out of time, so let's see here. I want to show you one slide here. So we're looking at 4 different sites. U.S. Wind, U.S. Wind, Maryland, Atlantic Shores, New Jersey, Empire Wind, New York, and then the combined Massachusetts sites. And we calculated the mean return period associated with different wind speeds, and you can tie that to hurricane categories. So this table in the lower right here shows the mean return period for those 4 different sites of a Cat 1, Cat 2, Cat 3, and Cat 4 hurricane. And it's important to note that a Cat 1, Cat 2, and Cat 3 hurricane for all 4 of those sites will include a mean return period less than 500 years and greater than 500 years, which is the design requirement in the current codes. So we get kind of full coverage when we study Cat 1, Cat 2, and Cat 3. So we have a whole process we developed in order to select characteristic storms. And so we have a characteristic storm for the Atlantic coast for Cat 1, Cat 2, and Cat 3. Another area where we're advancing what we were done previously is we want to know the influence of global warming on hurricane activity. So this is showing the historical record from for about 40 years of spawn locations in the Atlantic basin of hurricanes. We can see very clearly that they depend on some key parameters, such as, so red here is showing conditions that led to a hurricane spawning event, and blue is showing conditions that didn't. And so you can see that there's a key signature with respect to sea surface temperature, with respect to wind shear, relative vorticity, and relative humidity of whether a hurricane will spawn or not. And these 4 things are going to be changing. The IPCC scenario for the representative concentration pathway 4.5 tells us how these are changing, and so we can use this information to see how the hurricane risk is going to change. These 4 parameters are basically independent. And we're developing a model then to then consider them and how they'll impact hurricane risk. We're working on our large eddy simulations, so they're moving right along. They take a really long time. So you're looking at kind of a simulation on the order of 10 to 50 to 60 minutes, taking 400 hours. So computational resources are a huge part of this project and managing those. And we finished the Cat 1 and the Cat 2 simulations. We had to adapt to the computational demands by developing a quadrant-based approach in order to simulate just a quadrant of the wind field in order to make the computations tractable. And that's where we are. Yes, I'm just about out of time here. So just wanted to give you a taste of the scope of our project, the background that we're building on, and our preliminary results. So yeah, thank you very much.
All right. Thanks to all our speakers, and here's just a reminder of the Slido code to enter questions. We do have several that came through. We have about 20 minutes to go through some Q&A. So I had, in reviewing and thinking about the presentations today, I had a couple themes that popped out to me, and this has actually been echoed in some of the Q&A we got through the app. So I'm going to start, because moderator preference, I'm going to start with my idea. In thinking about scaling up some of the technologies you all have talked about, we got some questions specifically about, how we take the results or the technology at a particular place or topic and apply this regionally because of the policy goals and, eventuality of offshore wind, the size and scope of these projects and development up and down the coast. So for Dale, we got a question about, what about 150 turbines? How would that impact the scatter of HF radar, and what are the implications?
Is this on? Well, so with 150 turbines, what we were showing was just for 2. And what really is important is not so much how many total turbines are in the field of view of the radar, but how many are in a given range ring, which is about 5 kilometers. So anything within that range, the number of turbines in that is what makes the biggest difference. And as of right now, we haven't looked at anything beyond 5 turbines, but we're currently funded through another program. Actually, Anthony Krinsich in the audience out here is the PI on that, in which we're using larger simulated data sets with 50, 100, and going up, and seeing kind of where the breaking point is of all of our mitigation strategy and how many they can actually handle before they break. Because at some point, if they're all at different rotation rates, it'll just be complete noise. And we know there is a breaking point, but we just don't know where that is right now. And yeah.
Great, thank you. Super interesting to think about that at really large scales. So on this theme, this question is for Aaron. How are your initial modeling results in the Rhode Island, Massachusetts area comparing to the current continental scale density models that you spoke about?
So what we're seeing is a little bit more granularity. The other thing too is that we're seeing greater detection and higher density than a lot of the previous model methods developed by Duke. So they're relying primarily on visual survey observations, whereas we're able to integrate both the visual surveys and the acoustics. So we think that the Duke models are under-reporting species occurrence and density, and so these multimodal methods will probably, have higher density and higher abundance.
That's great, thank you. Are there any other panelists want to weigh in on the scaling up issue before we move on? No takers? Okay. We'll keep going with this audience Q&A because they're coming in and pretty interesting. So for sail drone, so for Carl, how do you account for increased background acoustic noise from a moving platform versus a buoy? And how does that increase, or rather decrease, your detection range?
Yeah, good question. Most of the buoys have between 1 and maybe 3, maybe 4 hydrophones. Our system's got 14, which gives us a fair bit more spacing and a lot more ability to beamform, which is essentially the ability to look down a narrow angle and say, oh, this is what's right here, and so I don't have to worry about all you people talking over here. I just want to hear what he's saying. So that's one way. And then the other thing is, compared to a vessel that's got an engine, we're silent. We don't make any noise. So you do get a little bit of flow noise, but it's a couple of knots. You're going to get that over a buoy in a tidal zone.
Totally. Staying on this theme and back to Carl and Aaron here on this, can you describe, so you described the technology you all are using are basically detections of marine mammals. Do you have any ability or, want to do in the future, seek to augment that with directionality or localization capabilities? And then building even more on that, a great question here about this, these are just detections. are there emerging strategies for mitigating impact to these species once you detect them that could be incorporated in the technologies and platforms you're using?
You want to go first?
Sure. So as far as the detections and localizations, absolutely. I mentioned that ability to beamform because of the number of elements, right? So that already gives us a bearing. And if you could fingerprint the animal, which is pretty dubious, or maybe you guys can, if you can fingerprint the animal acoustically, and you can move yourself, you can start to localize it. But I mentioned a lot of our work in this project is going to be ConOps driven, where we have not one but 2 or 3 vessels out there. Well, if you get 2 bearings, you've got a position. That's localization. And then I guess the other thing I'll add is we're fairly good at that because the lineage of the technical folks that are working for us. I spent a couple of years working at the Naval Undersea Warfare Center. My immediate boss has 35 years as a Navy submarine captain and squadron commander. So figuring out where things are underwater, his life depended on it. So, and as far as mitigation, I don't have a great answer.
So on the fixed platform and bottom-mounted sensor side of things, with the various projects that we've done, both in collaboration with the states and federal agencies, there seems to be a wide variety of survey designs, and to use the term strategy, I think would be overly generous. There's really little rhyme or reason for how sensors had been placed. The different projects had different reporting requirements. So for example, our efforts in the Maryland wind energy area and Virginia, BOEM wanted to be able to do localization based on triangulating signals, whereas for Massachusetts, that wasn't a requirement. So one of the challenges is that doing greater precision or greater sophistication with the data has a step function in cost, and so it's often a conversation both with the developer as well as the regulatory agency as to how those data want to be used. In some cases, presence-absence is sufficient. In other cases, localization may be helpful. The difficulty is that with something like localization from bottom-mounted sensors, you need to have the detection of a whale vocalization on 3 or more sensors. So what ends up happening is the array design ends up being more compacted, and then that can either decrease your detection range or requires a greater number of sensors to have a similar detection range compared to a spatially explicit survey design. And now, in terms of mitigation, some of the strategies with a lot of the technologies, whether it's piling jackets or bubble curtains, I think a lot of these are really exciting to see. What we're seeing in some cases are reduction of 2 or 3-fold in terms of source level. And so I think what we really need to have is go from not only the acoustic and sound propagation modeling of mitigation platforms for construction and actually start getting some in situ empirical measurements as well. And so I think the difficulty is that with the shifting distribution of things like right whales and arguably other cetacean species, being able to have both the seasonal strategy as well as a site-specific, construction mitigation strategy is ultimately where things are going to head.
Great, thank you both. Shifting now down to Rebecca and about fisheries. How do you anticipate your project will increase support for offshore wind from the fishing community? Will recreational and commercial sectors differ? And again, building on that, how do you envision the co-design and co-use framework being used by wider industry?
Yeah, so in terms of, it's working? Yeah? It's good, okay, thanks. So in terms of increasing support, what I've found so far in our experience talking with fisheries participants over the last couple of years is that there's a real opportunity here for sharing information. So talking with folks, depending on what types of gear they're using, whether it's gill nets, trawling gear, dredge-based equipment, and the like, understanding what their needs and requirements are, and then showing as well what those fixed offshore turbines and floating offshore turbine balance of systems might look like and what can potentially be varied. So I think by having that conversation where you're openly hearing about the needs and requirements based on gear and fishing activities and sharing what the options might be on the technology side, just allows for more of an honest and open conversation about what can be done in the future. And what was your second question, Emily? I'm sorry.
Is about the framework and if it could be applied and used by others with industry.
Yeah, so it was, I'm really excited about developing this co-design framework. It's been done in other industries, and so looking forward to developing it here. It was hard to choose just 2 case study regions in the Gulf of Maine and the Central Atlantic. But also having worked in the New York Bight with the other fixed bottom work, I can definitely see where you could move a similar approach around to other fisheries depending on what's valued in a region and which fisheries participants are open to having these conversations.
That's great. And this is, while we have you, Rebecca, this is kind of a clarifying question. The fisheries, I don't want to say interactions, the fisheries collaborators that you have, are any of them aquaculture types of fisheries? And had you considered in the project, considering aquaculture, this questioner asks, is it even possible to include them in floating turbine designs? I think it's been talked about with the fixed bottom, but can you talk a little bit about the potential co-use of those structures?
Yeah, so some of our partners, like University of Maine, are definitely thinking about aquaculture potential at floating offshore wind farms. You definitely get into a more complex number of like interactions when you're thinking about that. But I have heard of fisheries participants talking about other ways of not just via aquaculture, but potentially moving SPAD or whatever kind of changing kind of the larval interactions around the wind farms as well. So I think there are some solutions that are kind of outside of the box of just straight up technology solutions.
Yeah, cool. Let's switch gears again and go back to hurricanes for a little bit. So Andy, we've got a couple clarifying hurricane type questions for you. What would you say is the relative risk and importance of nor'easters compared to hurricanes?
Yeah, fabulous question. So I can't put a kind of number on that, but I'll offer a little bit of commentary. Just in one of our most recent working group meetings with the insurers and financiers, they told us how much more concerned they are about nor'easters for mid and North Atlantic sites, mostly because they happen when weather windows for repair are the shortest. So having damage in winter months, repairable damage in winter months, is a more significant deal than having in summer months because the weather windows are so much shorter for repair. Relatively speaking, the more north, the winter storms tend to be more important. The more south, the hurricanes tend to be more important. But it would be a fabulous follow-on study to actually put some kind of risk numbers on nor'easters, on winter storms, because they are an important part of the risk profile.
Are the differences simply seasonal, or are there structure of the storm differences that would be unique to nor'easters versus hurricanes that might be worth, exploring?
Seasonal and winter storms are just bigger. They're kind of, hurricanes tend to have a more defined structure, and nor'easters are larger. They have a greater kind of extent. That has an impact on wave loading, which is a huge part of risk of structural damage to wind energy infrastructure.
Very interesting. Couple more on hurricanes. Will your work finish in time to support the 2030 30 gigawatt goal?
Oh yeah. This is so this is a 2-year project. We're 3/8 of the way through it. We hope to have some kind of actionable outcomes that can be incorporated into the codes that will govern the design of these structures. So yeah, definitely we plan to be well in front of the 2030 goals.
3/8 through the project. That's very precise.
Well, I just did a quarterly report, so yeah. It was two days ago.
Perfect.
So.
On your project, Andy, are you also looking at reliability impacts if turbines have to be proactively turned off as storms approach in order to limit long-term damage?
Yeah, so I mean that's the standard operating procedure, is that if you see cutout wind speed to usually 25 meters per second, that you shut down the turbines during the storm. So that is a part of overall downtime, a part of the cost of energy, a part of the kind of overall resource of power generating capacity. But it also is a key part of mitigating, of shedding load so that you can avoid kind of more long-term damages. Any kind of structural damage that happens to these turbines, I mean, we saw earlier today the repair vessels you need, the installation vessels you need to install turbines, all the supply chain you need to set up. It really only makes sense to do it once at the start of a farm. So to repair one in the middle of an operation really isn't a viable situation.
Yeah. Okay, so one last one about hurricanes just came in. Will any aspect of your risk assessment be applicable to the Pacific coast or the Gulf of Mexico?
Not with this project. No, yeah, this project is strictly Mid-Atlantic and North Atlantic.
Okay.
But another great follow-on study. Yeah, winter storms, Pacific.
Okay, it is extremely challenging to find a question that's broad enough that all of you could provide an answer because this is such a diverse group. So I'm sorry, Andy, this might exclude you a little bit, but folks are wondering, this was in the context of just the marine mammal work, but folks are wondering, are there lessons learned from European offshore wind farms that are relevant to your work and how we assess impacts and coexistence? And I don't think there are equivalent storms in Europe that Andy could speak to here that are affecting wind farms out there. But maybe as our closing, we have 8 minutes or 7 minutes or so. We could just go down the line and you could speak to regional scale and broader and lessons learned, like kind of send us out with like the big picture. Go ahead, Dale. Start us off.
So mine's pretty easy. There's not, right now there aren't currently other wind turbine field or offshore wind turbines with radars operating with them. Previously there was over in Europe, and that system was later shut down. And yeah, so there's not a lot that we've taken from that other than identifying kind of the impact initially.
Okay. And do you want to weigh in?
Just a brief comment. Yeah, so I mean, Europe has storms. They have a 40-year history. The insurance companies that are on our board are all the reinsurers for the European farms. So they have experience with what happens when damages happen and operation is disrupted during storms. So that is for sure relevant experience. I had one more point to make, and it's escaping me right now. I'm forgetting my last point. Yeah.
So there's been quite a few lessons learned from the European experience. Certainly, there's been sound underwater does weird things, particularly in shallow water environments, and so being able to understand how is noise generating processes, how does that reverberate and propagate. There's been a number of studies in and around the UK that have helped answer that question, and a lot of those things like source level and propagation distance are being used in our thinking in terms of what's happening over on the western side of the Atlantic. The part of the difference and part of the challenge has been the species assemblages are different between the western and the eastern sides of the Atlantic, and so for things like dolphins and porpoises and some of the what we call odontocetes or the toothed whales, there's quite a few of those in and around Europe, and so that's really helpful to apply. But Europe lost its baleen whales during the era of industrial whaling, and so there's still a guess as to what is going to happen, if anything, with things like pile driving and baleen whales. I think the other thing that the other opportunity not only comparing the European experience with sort of the North American market, I think there are opportunities to look at other emerging wind energy markets, whether that's Australia or South Africa or South America, where there are other baleen whale species. So for instance, southern right whales are not nearly as imperiled, if at all, compared to North Atlantic right whales. So in terms of being able to understand and infer or predict what are impacts to North Atlantic right whales, looking towards the southern hemisphere and lessons learned there might be a particularly exciting opportunity to explore.
Yeah, I would second that, but slightly add. The Europeans have done a pretty good job of developing the passive acoustic monitoring over the years. In fact, that PAMGuard interface that I was mentioning, that's often kind of the standard for a lot of people to use, is primarily a UK product out of a couple of universities over there. So we've looked at what they've done, and we've certainly talked to them, and they're also certainly a competitor. There's no lack of very capable European uncrewed vehicle companies, so definitely looking at it.
And on the fishing activities side, activities are very different, obviously, between Europe and the United States in that regard. I will say for our NYSERDA fixed bottom fishing interaction studies with the scallop and surf clam ocean quahog fisheries, that we learned a lot about the impacts of different types of scour protection and inter-array cables, what you could do at cable crossings to help with interactions with dredge-based fishing gear, the types of O&M and inspections that would be needed to understand what's happening around the turbines and with the inter-array cabling to ensure that fisheries participants know what's happening out there as often as possible, so that they know how their gear might interact with what's in the seabed or buried below the seabed. So we have learned, I would say, a lot from Europe in that regard.
That's great. Thanks, everyone. We're just 2 minutes ahead of schedule, but I think that was a really nice way to wrap up. Thanks to all the panelists. Join me in thanking them. You have a few words, Julian? Thank you.
Yeah, and thank you, Emily, for the thoughtful moderation. I really enjoyed the discussion, so thanks. Yeah, just a reminder for tomorrow that we are going to be in a different building in a different room to kick off. The networking breakfast starts at 8:30, and the building is the John D. O'Brien African American Institute, and the room is the Cabral Center. That's on your schedule, and then the first keynote starts at 9 a.m., so find your way there by then, and we'll see you all tomorrow. Thanks.